Okay. Okay, CBR. Yeah, that should be fine. That's good enough. Bam. Live VOD desktop mic. Let's make sure that lines up. Live VOD desktop mic. Okay. Wow, that was a good stream quality there. You like that? Okay. What have I missed now? I hit F5. Did I lose chat? I probably lost some subs. Okay. Let's see. Does it work? Does this work? It says 6 kilobit on my side. That's a lot of bits. Something deep inside that I cannot see. Okay. Alright, is there anything else we should do? We should add Twitch to this stream, right? Twitch, chat, OBS. What does everyone use for it? Cap chat? Get it? My name is Gamozo. Let's not turn on fade out because we don't have any people in here. I think I do like the Sonos theme is what I've done in the past. I don't know. This is gonna be pretty good, I think. Add. Oh, thank God I have browser sources and I don't have to add that in. Okay. Uh-huh. Okay. Alright, this is gonna be fucked first. Okay. If you can't read that, you're blind. That's not what I didn't want to do that. Alright, say something, chat. Jesus Christ. What is this? Snooze chat? And then cap chat, remove gradient. I'm pretty sure there's a way to get rid of the annoying gradient thingy. I don't know. We'll put chat here today, okay? This is where you get to go, all right? You're in jail. Okay. What else do we have to do to make this a professional stream here? Anything else? New apartment? Nah, it's the same place. Just move the desk. Streamer should tell us what Minecraft texture pack he was using for the first part of the stream. It was actually Terraria. That's why it was 2D. You fucking idiot. Okay, did we do everything? I remember when Gamozo was a hot tub streamer. That's fair. That's fair. That's kind of rude to bring up, you know, the past, things that aren't in my control or not. Like, I can't just stream if I feel like it. I gotta get approval. Let's see. Why is everyone taking low bitrate photos? Oh my god, you guys are so toxic. Wow, it looks so bad. Everyone's so mean. I just came here to give it a nice stream, and everyone's just, the stream quality is 6 kilobits a second. Okay. And let me, I think the mic is facing the other way a bit. Let me adjust it. I like this. Why did I have to tighten it so much? Oh, there we go. Okay, okay. Can you hear that, chat? Just making sure. Press 1 if you can hear that. Can you hear that? Anyone here wearing headphones? That wasn't very loud, actually. Yeah, that's because I've got a compressor in. Okay, now... But I need it off to the side. But that's like... I fucking hate this stand, dude. It sucks so much. Okay. Can I see everything here? It's kind of ass experience for me. Okay, I don't like this big ass mic in my face. Hello? What other options do I have? Okay, I can do that. But I don't think it will stay down, will it? I hate this stand, chat. Yeah. Can I go under? Oh my god. Oh my god. Oh my god. I think I'm going under. Huh? But now it just needs to not randomly rise up. Huh? Huh? A little under? It's a little close to my face. Your compressor seems to be working very well, actually. I'm very glad because I randomly dial it in like 2 minutes. Normally, I try and do like a lot of testing here. Hi, Bloomus. Make it not rise up, duct tape some weights, yeah. I fucking hate this. I've like done a bunch of adjustments on it and it just never... I don't know, maybe I don't know how it works. Maybe I'm just a dumbass. That's okay. Alright, so... Welcome to the stream. This is actually not bad. It's not... I can see 3 of my monitors. I lose 1 monitor with this stand. Okay. Alright, so... then we go like this. Huh? Okay, I gotta go get a slime so I can train. You fucks. I killed the slime earlier on accident. I didn't mean to. I'm sorry, chat. Let's go get a slime quick. We'll go like here. If you put it to the side, we'll hear you okay. Yeah. Ultimately, like, if you don't have the mic up in your business, it's always gonna be shit. There is like no workaround to that. If you want any good mic, you have to have it inside your mouth. That slime had a family, yeah. But how's everyone doing today? Is everyone being good? I don't know what I've missed. Hype Train, Desu resubbing, Emma Byte using a Twitch Prime, Zainab Lena with the 44 months. chatting all over your body? Yeah, I mean, that's just, do you not like that? Do you want the chat down here? Oh my god, you guys are so fucking needy. I want to see the streamer. No, I don't want to see the streamer. I want to see the code. Oh, I want to see the streamer. Oh. Someone needs to make a Twitch draw instead of Twitch chat so you guys can communally draw mustaches on my face. Is this Tibia? Yeah, this is. Of course it's Tibia. It's the only game I know how to play. Those won't be mustaches? Oh my god. It would be mustaches. You guys are not toxic, okay? I think the average chatter would draw way more than I'm... No, my chatters are good. Raise your hand if you've had only one intrusive thought so far this stream. You can't say that about many chatters. And I think this stream can do that. Okay. Okay. Deafening silence. See, Nikito's good. Definitely not Nightshade. Alright. This takes like 5 minutes to set up and then we'll do some dev. Torch. If I get a malware on my PC and I don't get it out instantly, can it survive on my keyboard, which has onboard memory? I mean, theoretically, yes. In reality, no. There's not going to be any malware that's going to be targeting some random person that's doing that level of persistence. Unless there is specifically a keyboard worm going around, in which case, then, yeah, get fucked. Be extremely specialized, yeah. Keyboard would have to be vulnerable. I imagine most keyboards are probably exploitable. I imagine that's not really a secure-ish boundary. That being said, a lot of hobbyists actually care a decent amount about security, like small, like niche, like if someone made an RTOS in Rust and that's like what is taken off as like the firmware everyone's using in their keyboards, then in theory it could actually be pretty good. How do you hack a keyboard? I mean, ultimately, like a lot of keyboards that are customizable, it'd probably be over the customization protocol. Like where you set LEDs, you assign macros, you tell it scripts to run potentially. That's probably where there would be bugs. A conventional keyboard, like a 2000 keyboard that's like USB 1.1 just came out. I didn't even think they have firmware. I'd imagine that they would have like a serial shift register to output fucking USB and like that's it. I don't even know if they would have anything. Too many security incidents lately? Oh, interesting. I don't know. I've never really followed like malware and security stuff. I have no idea like when things are hot and spicy or when things are bland as shit. Come on. No. Too many fake security incidents? I mean, there's always going to be that. It's pretty common that people who are like probably going to be good at some point in their life don't know how to like handle an issue really early, and they like don't do the PR correctly. I genuinely don't think a lot of the like overhyped bugs are malice. I think it's just people who, I don't know, want to feel proud of the work that they did. I'm sure sometimes people intentionally overhype them, but I genuinely think that a lot of people who like hype up bugs or like don't know what they're talking about in security just genuinely just don't know how it works, and they actually think that whatever they did is novel. Giatano's super proud of his work. Yeah, I mean, fucking shout out to him. Fantastic work. Though people are worried about firmwares and cheap Chinese keyboards being backdoored, where it could keylog in the background and periodically send it out using keyboard shortcuts to open a terminal. Man, I feel like that would be very difficult to do at scale because people would just notice. Like, I would notice if a terminal popped up. You don't really have good mechanisms on a keyboard to like know when a user is away. Obviously, you can just go when there's no key presses, but that could just mean it's like someone with it up on another monitor. I feel like that would be a really, really hard op to run. You're probably better like requiring the user to install some drivers or software to like modify the keyboards and add macros and stuff. Doing that fully generically, I think, would be really hard. Doable, obviously. Like you can basically run any op you want to run. It's just gonna fucking suck ass or like be way more effort than an alternative. I doubt any keyboards are actually doing that. Yeah. Keyboard communities are worried about it. I could see that. I mean, it's just fun. Like, there's a reason why like so many people at like a DEF CON like love doing all sorts of like paranoid like crypto and shit and like open source firmware and security. It's fun. It's if you genuinely think that you're a target to an attack that like any of those sorts of things actually fucking matter on, you're fucking delusional. But it is fun to like imagine that you're really important or that you have like, I don't know, just a leg up compared to other people and like smarter, better at security or whatever. In reality, like what's your fucking threat model? Come on, slimies. Imagine plugging in a keyboard and ask you for your Wi-Fi password. I don't know. I feel like that's just going to be pretty standard. I could see keyboards pretty quickly becoming just like Wi-Fi and not like dongle based. I mean, like my nice keyboards, I don't know if they use Wi-Fi, but they definitely are on 2.4 gigahertz. So I don't know what protocol they're talking on that. Come on, slimes. The mama slime is not here, so come on, mama slime. What do you think about the Linux cup service? I mean, it's old school Linux. It's like Unix shit. You know what that means. You know the code quality is gonna be dog shit. But I'm sure it served a purpose when it was the only way to print things. Making a gooey mess over the city. Yeah. Get in here, slimes. There we go. Okay. Bink, 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 bink. Eat my food. Heal up. Attack the slime. Okay, what else do I have to do? Is this all I have to do? Can I just stream now? Oh god, I gotta turn the font size up. I'm blind. I'm a Twitch viewer. Okay. We'll resize this to there. And then we'll put the chat right where it is. Maybe we'll put the chat like here. There you go. That's where you get to go, chat. Press 1 if you don't like where the chat is. and I will just ignore you. Okay. It's not Wi-Fi? Bluetooth? It's definitely not Bluetooth. Bluetooth sucks. No one likes Bluetooth. Okay, what else do I have to do? I use Bluetooth for my keyboard? Yeah, because you're a fucking noob. Like, come on, obviously. Oh, I gotta resize. So, like, there. It's a 2.4 gigahertz protocol. Most keyboards and mice use as a low latency alternative. Yeah. Don't even think it's compatible. Yeah, I would imagine it's just YOLO over the protocol. Okay, chat. Hello. Today we're going to be writing a Verilog program to parse this signal. It is the signal that is used to read the ADC from the ADC. You get the digital bits. If you don't know what an ADC is, it is an analog to digital converter. So it takes in an analog voltage and it tells you what the voltage is in a digital bits. This is like basically how a multimeter is made. But you can get these for all different speeds and precisions, and you can get them that run really fast and allow you to sample a shit ton of stuff, and you can make an oscilloscope out of them. You can get them that are really slow, but like have higher accuracy. Effectively, like the faster you run them, the lower the accuracy, because the smaller the window, the less time you have for like charge to build up in circuitry, the more susceptible you are to noise, like those sorts of things. So, I picked out this analog to digital converter for a project that I have, which is reading a linear scale. Mi to Toyo AT113 is the scale that I have. And there's like a million different manuals for this. We're going to try and hopefully find the data sheet that you and I like the most. And by that, I mean the one that I like the most. The problem is there's like a million of these. And most of them suck. Some of them are really old. Some of them are really new. Some of them are not accurate. Like this one I think is old, but I think it contains the most information. This is just a different one that probably contains similar but different information. This one's not my scale. That's a 1300. This one is also old, but also has information in it. Yeah, so hopefully all three of these will kind of allow us to go through this problem together. How does that sound? Press 1 in chat if that sounds good. Have we set up the stream correctly? Is the microphone good? Are we clipping? Is it left ear or right ear only? Is the video quality ass? Are you just whining and bitching because you're a chatter? I'll wait. Dead air is good for live streaming. Why do you need to read this data? Yep, that's what we're going to get into. Just want to make sure everything's good here. Yes to all. Is this First to 11? Yes, this is. This is Decode by First to 11 and covers Volume 3, 2019. Oh yeah, can't I like get that information really easy to display? Like what the song is now? Because like there's some Linux protocol where it just all that goes. I don't know how. But it like goes somewhere. There's like some protocol that like has that information. I forget where I like randomly saw it on the computer once. MPD? Nope, not MPD. The audio is inverted. Now there's some like place that Linux applications can say that they're playing music and information about it, and other things can pick it up. It's like sitting off dbus or something. Man, I forget like what app. I was using some like random app, and it like was telling me, oh, was it, Mango HUD. Mango HUD can display it. Mango HUD, Mango HUD, Mango HUD. What can I open? Do I have Xonotic? No. Mango HUD, DLSim, wine config. No, can't do that. What do I have? What do I have? What do I have? Wine, shade cores, this. Oh, I see. I've updated wine. Okay, we can't do that one. What else? 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 I don't know. Mango HUD has the information. I don't know where it gets it from. Mango HUD audio playing information. I don't know. Someone brought it up, like where it came from. Where's the config? Audio playing, play. Media? Yeah, media player metadata. I think it's this. I don't know where it sources the information from. Check stream chat. Okay. There's a shell script. Virus.sh. Chmod plus x virus.sh. Virus.sh. QDBus. Okay, I don't have the QDBus program. What's that in? Sudo emerge QDBus. It's gonna be in some random fucking package, right? Okay. Let's see. The operating principle is super cool on these scales. Yeah, we're going to get into that. It is something I like. It's very much like something that I am excited to do. With just projects of my own. Okay. Virus.active player. I'm putting this. This is just a file I was putting it out to. This is telling me that Firefox is playing music. It's not telling me what the music is. Wow, that sucks. It's trash. It's trash. Do better, Desu. Thanks for trying, though. Yeah, I don't know where Mango HUD gets it from. Someone at one point in Discord, I think, said or where it was from. Media. Get media player metadata. Go to the definition. Go to the... Where's the implementation? Get dbus player property. We can probably still do it, right? We can still do it with this shit script that he gave us, virus. Is this in Empress? libdbus. I imagine this QDBus is just gonna let us like do stuff. I probably shouldn't run this command on stream. It's probably gonna like leak information. Yeah, so like things show up here. New method call, Empress Media Player 2. How would I do this? Command line. Get name owner, get player property. Select active player. Filter signals. So is this called Empress? Empress, sway, current media. Like, surely. Waybar component, Empress 2 compliant media player data, widely supported Chrome, Chromium, Firefox, other browsers, VLC, all this sorts of shit. I already have my own script for doing my sway. Oh, I think I lost it actually. I think I only have the binary. I mean, I'm sure I have the source on like a old hard drive. How do I just get it? Manually use dbus. What's this? What's this? Can I use this command? Spotify wasn't found. Yeah, that makes sense. Okay. So I can use the old script, which will tell me where music is playing, which is this Firefox instance. And then I say player. Player dot method. What method? What method do I want to call? Dude. Player control? Player CTL? Like, surely there's something that can just output it to the fucking command line, right? Like, that's all I want. I just want an existing tool that just poops this out to the command line. Supported clients. Empress player control to control them. Tell me about this script. It's got a change log. That's cool. Output current track metadata. All right. We're just gonna grab this whole script, right? Hey! It worked! Okay, Eric calling start service by name notifications, SIG11. Oh yeah, my notification daemon is like crashing all the time. I don't know why. Like, it's just constantly crashing. Quiet notification. Hey! There we go. Okay. There you go. So we can now run this script. Do I have a local bin in here? No. Local bin. Let's just move this to cargo bin. Are you serious? Obviously, cargo bin has to be in here, right? Where the fuck did I put it? Am I an idiot? Hello? Oh, I moved cargo bin. Local bin. Nice. Okay, so I can do that. But where do I put it? I can't put it in my bar because I'd lose my old information in there. And I like the information I have in there. And apparently I don't have it anymore. I don't know how I removed it. But yeah, I have no idea where I put my sway bar code. It's very sad. Putting in a file? OBS text from file. Okay, I like that. How How do I run this in a loop? How do you do a fucking loop in... Do I want to do a loop in sway config? Can I like do something like execute every X time? Wait, is Waybar Folk Python? Yeah, it's just Python. Jesus fucking Christ. Of course it is. I don't know why I thought I wrote that in Rust. Cargo bin empress player control -q. Okay. Get current media. Media is equal to sub process check output. Okay. I don't know how pathing works, so let's just hardcode the whole thing. And put -q, and then we'll put this in. We'll put this out front. And there we go. Okay. Error with status command. Okay. Okay, we got a new line and we got bytes. How do we, is it trim or strip? It's strip. And then we want decode or encode. I always fucking forget. Decode. There we go. We did it. Now I just have to put this down. And you guys can shut the fuck up about what's playing. There you go. Was that fucking hard, chat? Jesus. It's actually really nice. I've kind of wanted that. Woo! We fucking did it, chat. Let's go. All right, let's see. What have I missed? Julian C, thank you so much for the 13 months. Hell yeah, brother, man. Anyone have points to rewrite in Rust? No. No. Dude, I'm so sick of Rust. I love it. I'm so sick of it. I'm struggling to write code. Yeah, because I don't want to write it in Rust. But it's the only language I can write code in right now. Because I'm not going to write anything in C. So I just need to make S-lang, chat. It's really not that big of a fucking deal. We'll just make C, but S-lang. Add some lifetimes. Okay, let's make sure the size is good. Is this webcam too big? I don't think so. S'mores is sleeping down there. Can you see S'mores? Kind of. He's a good boy. Yeah. Are you a good boy, S'mores? Yeah, you're such a good, cute boy. You're so fluffy. You got groomed today, S'mores. You got a groomer today. Yeah, you're such a pretty boy. I'm so proud of you. Do you know how important you are to me, S'mores? Yeah. Good boy. Enjoy your nap, Bubbo. Have a good nap. He is the best. He just sleeps right behind me. He just lays there. And I'll get up, he'll play, I'll bring him outside, take him on walks, and then he'll sit behind me. This is our life. And then we'll cuddle in the morning for like an hour, cuddle at night, cuddle during a nap, cuddle during watching anything on the TV. S'mores knows that like when I brush my teeth, it's time for me to go to bed, so he gets up on the couch, preps. My cat does that, and sometimes my chair will step on her tail. Yeah, I am extremely cautious about it. Watches this stream, I just run over S'mores. But I'm very aware that he's always behind me, because he always is. There is no alternative. Okay. Welcome to the stream. I know we went on a tangent, but now you have the fucking stuff. Are you happy? Are you happy? You get your little stimmies. You get to see. Anyways, today we're gonna be working on a project I've had for a while, which is writing a reader for these linear scales, and this is a project that I kind of wasn't expecting to do. Mainly because the DRO that I have is fine. So let me explain kind of this whole situation. So these linear scales are used to determine the linear position of something, which is the head of the reader. So what you'll do is you'll bolt this scale. I'm trying to find out like better photo of the scale that's not like a fucking diagram. Surely there's a good one. Surely we have a good one. Man, they're not doing a good job of selling me on buying this because it's not telling me what I can use this for. Anyways, here's a linear scale. Whatever. So you'll attach down the like bar piece to equipment, and then you'll attach this head to another piece of equipment. You'll have to build, whatever brackets. And when one of them gets displaced, this will record the linear position of that. So really all it's doing is it's telling where this head is, this reader head is, compared to the rest of the scale. And there are many, many, many ways that you can manufacture and create these scales. I obviously went with a fairly high precision one that was also still like slim and would fit on my machine, which is this AT113. And the AT113 is one of the optical scales. Other scales usually are like a magnetic scale, but this is an optical scale which uses these operating principles. And effectively what you have is inside of that scale body, you have a piece of glass, just this small piece of glass. It's like about the same size as like a test slide if you do like biology, except it's thicker, obviously, just for rigidity and so it doesn't break. But it's a pretty small piece of glass that runs down the entire scale. And it has, I don't know, somehow laser etched in, it has these vertical lines evenly spaced out exactly 20 micrometers apart. And 20 micrometers is rather large. It's not super, super tiny. That is very close to like 1/1000th of an inch, which is like very visible with the naked eye, whatever. It's you have basically this grading pattern on this piece of glass. Now, my, linear scale with my DRO allows me to get 0.1 micrometer resolution out of this. And the question is, well, how does it do that? How do you have a 20 micrometer grid? I call it a grid. It's really just linear lines, but a grid is just kind of easier for me to say, I guess, but it's not actually a grid. So you have this 20 micrometer grid, but you want to get more resolution than 20 micrometers out of that. So how do you do that? Well, it's done by determining the interference pattern between the scale and a piece of glass that sits in front of it. So what you have is you have this LED here and a collimator. And if you don't know what a collimator is just trying to make all of the light be super parallel. So if you think about like a flashlight where you have like the rays coming out and splitting into like a Y shape and they're kind of all over the place, that means you have light rays that are kind of going at all of these different angles. And a collimator is just going to make all of those light rays parallel. So it's going to like take probably a very small like laser LED. It's going to expand it out to whatever width it needs, and then it's going to go through a collimator lens, which is going to effectively just reject non-parallel light. There's not really a great way to correct it. You just get rid of the ones that aren't really going straight, and now you have effectively all of the light coming through parallel, which means it should be going straight through these gratings on the glass scale. And then you have another piece of glass that also has those lines on it. And then just imagine right? Imagine the interference patterns when you slide these sets of lines against each other. Obviously, when they're perfectly 180 degrees out of phase, it's like fully blocking all of the light. And then when they're perfectly overlapping, all of the light is coming through, or at least half of it is, because half of it's cut off by the gratings itself. So effectively, this ended up producing this sinusoidal pattern, because the more and more that they overlap, the more and more light is allowed through. And this is just a common way to kind of control the amount of light that comes through things in various different stuff. So that means that you actually get these sine waves, these 20 micrometer apart sine waves, as output. Now, this goes through like an interpolation circuit, which is more about like how it's actually determining like where the position is. I don't know exactly where it actually, or how it does its interpolation. My scale doesn't output a digital waveform. I know that there are some of the scales that Mitutoyo produces, some of the pins on like the D sub 15 or DB15 connector have those output things, but my AT113s do not have that. I only get the sine wave output. So this sine wave is 20 micrometers peak to peak. Basically, when you displace the scale 20 micrometers, you start a new cycle of the sine wave. And there are two receivers on it that are both 90 degrees apart. And I don't know exactly how they did that. I imagine that they literally just have two LED receivers, and one of them is very precisely positioned to be that distance apart. I'm not 100% sure. I'm not sure how 90 degrees they are. I don't know if it's like, it's just two phases, they're approximately 90 degrees apart, but it's, those two phases are just used to determine like position and direction. Or I don't know if you can actually rely on them being exactly 90 degrees apart such that you can then get more information. Basically, you can go down to 5 micrometers, because on the rise and the fall of the phases, like if these were perfectly 90 degrees apart, then you could rely on one of them when crossing through 0 is you have moved 5 micrometers. So I'm not 100% sure on how they do that, but this is supposed to output a 1 volt, a 2 volt peak to peak sine wave. So it goes to plus 1 volt with respect to a reference to minus 1 volt with respect to a reference. So this scale takes in 5 volt power, ground, and it produces a reference point at 2.5 volts. The sine wave then goes from that 2.5 to 3.5 and then down to 1.5. So effectively, 5 volt is the top. That's the highest power, the highest voltage that exists in that circuit, unless they're doing like voltage multipliers. So 5 volts is the highest, ground is the lowest, sine wave is centered around a 2.5 volt reference that the scale gives me. So I give the scale 5 volts of power and ground, and it gives me 2 sine wave outputs. It gives me the reference voltage, which is 2.5, but I imagine internally it could fluctuate, but that is the actual center line of the y-axis according to the scale. And it also gives you some like error stuff. So like if it's not sensing enough, or like you're not getting enough photons through to trigger the scale to like, I don't know, actually activate the receiver diode, an error light goes out. It's just a signal line that just gets pulled low. So does it have only one light sensor? It has to have 2, I think. Okay. Waking up to a stream on my day off? Oh, hell yeah. Bro has eyes that see the 1/50th of a millimeter. Yeah, it's really easy to see 1/50th of a millimeter. It's very easy to feel it as well. Okay. So, that leads to, why are we doing this? A, it's a fun project. It's just a curious thing I've had. B, I have a digital readout, and I have both a 2-axis and a 3-axis digital readout, and these are digital readouts here. Sorry for the pixels. I don't really want to find a better one. So I have a 2-axis one for the lathe and a 3-axis one for the mill. That's very common because on a lathe you only have 2 degrees of freedom, and on a mill you have 3. Technically you have like rotational speeds and all sorts of things. Okay. So effectively, on my milling machine, and we're just going to be only talking about the milling machine today because that's what we're working on right now, and it's the only machine I actually have working. It takes in 3 of these scales. So I have 3 physical scales, one on the x-axis, one on the y-axis, one on the z-axis. They then connect using a DB15 like parallel port style connector, plugs into the back of this scale, the back of this reader, and I have 3 connections to 3 different scales, and then this outputs in millimeters or inches all the way down to 0.1 micrometers where the head of the scale is relative to where it was before. So this is not an absolute scale. Some of the magnetic scales are actually absolute scales, but this is a relative scale, which is okay as long as you just never power down the machine. It doesn't lose track, and I think the existing one actually saves its position, but I don't know what happens if you move it while it's off. I think you lose count. Basically, losing count is a big deal. If you miscount, you are permanently accumulating that error. If you do not catch the edge of a sine wave, your scale is now 20 micrometers off forever. So, Desu was asking, why are we doing an FPGA? And that is the specific reason. I don't particularly trust, at least like Linux, maybe like a custom RTOS we'd make would be fine, but I don't particularly trust Linux to give me a real-time enough system that causes me to never lose count. Because if you lose count, you might scrap apart because your dimensions are just fucked and you're relying on the scales being accurate, or you recognize that they're no longer accurate, which by that point, something has to be quite off for you to notice that it's off, because you're not going to notice it's off even by like maybe 0.1 of a millimeter is where you'd start to like eyeball, be like, this seems way off from where I drilled the hole last time. But losing count is a really big deal. And these scales are rated for 120 meters a minute. So these scales can, with this DRO and these scales, so like the scales, the way the scales are physically designed allows the reader head to move at 2 meters a second, and the electronics of the DRO are capable of handling the signal output at 2 meters a second, which is very fast. It's 100 kilohertz sine wave. Even though that's obviously not like crazy fast, that's fast enough that if you stumble for even a millisecond, you have lost count. So I'd still say an FPGA is overkill, yeah. Yeah, I mean, you can just do it with like a real-time microcontroller, but I also want this to interface with HDMI output and display stuff and be able to make a graph and do timing information and communicate with Linux and use an Ethernet port so I can log my machining process and like have a record of what I've done and hook up other servos and controllers and components that might have a higher frequency. Like, there's just a lot. How do you navigate to workspace 33? It's just monitor 3, workspace 3. Does it have to be an all-in-one? I mean, that's the nice thing, is that the board that I have has everything. This has HDMI out. It has power supplies that can supply power for these scales. It has an ARM controller, an FPGA, a bunch of GPIOs. It has an Ethernet with gigabit support. It has an HDMI out. It has USB UART. It has a USB OTG. It has, like, but it's still fucking tiny and has 4 easy-to-support corners, so I can machine a box that holds it in. It's all passive. I don't need active cooling. It doesn't use particularly high power. It doesn't need a, like, crazy high power supply or anything. It is really, really, really nice for this. It's $200. I don't know why this is such a big deal. It's cheap as shit. It's a D10 Nano. It's really not that expensive. These DROs themselves are like $1,000. I think I paid $200. Maybe I got a deal or a discount. I'm not sure. I bought 2 of them because I'm going to make probably 2 DROs, and then I'll just keep buying more as I have projects. I'm just going to use it for like every project. It just boots Linux and outputs XFCE full Linux display and has a way of communicating between the FPGA and the SoC. So I can just make a GTK Python fucking display app for the DRO or a web page, and I can use the FPGA to handle the real-time processing of the signals. So I can spend 0 effort on the UI and get a good UI and a reliable like HDMI to a proper monitor that like allows me to output like a graph or 60 frames a second, that sort of thing. And this is the only thing I need. Technically, I need to put my ADCs on like a daughter board, but that's fine. I need to put 2 ADCs per scale. So I'll probably put 10 ADCs on this board, 10 8-pin dips, fucking tiny, just put them in a line, pin them up to the GPIOs, give them power, done. So, super, super easy. Okay. All right, so we need to process this sine wave signal. So I've decided I was going to use like an interpolation thing. I had op-amp set up as a comparator to give me basically a digital signal of at least when it crosses through 0. So when these sine waves would cross through 0, the comparator circuit basically when one is higher than the other, it's going to output digital 1 high. And vice versa, it will output low. I'm just going to go directly to the ADCs. From an FPGA perspective, 100 kilohertz is a fucking joke. So we can easily just actually sample the ADCs in real time, and that allows us to do slightly, I think, better processing because we can build what is considered a Schmidt trigger in the digital space. So a Schmidt trigger is a really common, I think a Schmidt trigger is specifically like the diode implementation of it, but the actual thing is common in all sorts of signals and industrial automation, which is effectively the activation threshold is separate from the deactivation threshold. So instead of having my comparator that when this crosses over the 0 point in the y-axis, it triggers high, and when it crosses under, it goes low. The problem with that is this signal is not perfect, and the op-amp or the comparator are not perfect. So you're going to get choppiness on this boundary because it's just such a sudden change that the circuitry might switch between on and off a bit, and that could cause issues depending on how you're sampling it and filtering it and whatever. Also, a 100 kilohertz square wave is way higher bandwidth requirements than a 100 kilohertz sine wave. And that's because a square wave is composed of the underlying waves and then a shit ton more stacked up at higher and higher frequencies to basically add those corners in. So what I'm going to do is basically write the software to control the ADCs, and then the ADC output will be able to trigger on, instead of at 0 crossings, we can have a 100 millivolt crossing triggers the like up, and minus 100 triggers the down, and then we can put like not have to really worry about any noise at those boundaries because there's not 200 millivolts of noise. There's probably sub like 1 millivolt of noise. I think maybe like 10. We'd have to like calibrate it to like see how much noise we actually want this to be tolerant to. But effectively, we need to write the circuitry that can talk to the ADC in the first place so that we can capture these waveforms, digitize them, and do some processing on them. So before we even think about the actual concept, we need to talk to the ADC. And the ADC is talked to through the SPI bus, just a simple serial bus, and we're going to go through that, what we picked. I'm going to read up on chat, bring up on things. Catch up on things. Magnetic scales must be more expensive. I think they are typically cheaper. They're definitely more common, more prevalent. They're also often lower resolution. these glass scales are typically going to be used in machines like positioning systems, laser positioning stuff, saws for cutting, silicon dies, like IC fabrication, that sort of realm of stuff. They're not really meant for like mills and lathes. Maybe you would use them on a like surface grinder, like a higher precision process, but obviously on a milling machine, you're not really going to get better accuracy than like 10 micrometer. That's going to be like, you can probably do better if you really spend a lot of effort. But most things are going to be finished to like 50 micron on a milling machine, 10 micron on a lathe, and when you want to go below that, you're going to use grinding or some sort of like slower abrasive process for the fine finishing work. I obviously just enjoy trying to see what you can do. If you really put a lot of effort in, like how many variables can you eliminate? And what I'm curious in is like how accurately can I machine things on a standard manual Bridgeport milling machine? And that's kind of why I want to play around with this stuff. So, what's really cool is that once I actually have this information digitized, I can then record it and do stuff in response to it. So these DROs can output serial information about the readings on the scales, but that information, I'm pretty sure, has to be triggered. And second of all, it runs at like 38 kilobaud. I can't remember if I can change it. TLDR, I cannot get much information out of the DRO. It's arguably the same difficulty to drive the scales manually than it is to process the DRO output, and at least this I get full control. I can do more interpolation, I can do less, I can do filtering, I can do compensation for damages to my scales. Like, there's so many things that I can do here. Obviously the DRO is way more suited to like an actual machinist because it has a bunch of functions and just works like every other DRO that's existed for the past 50 years. But I care more about having access to the raw data in real time, because I'm pretty sure that 2 meters a second likely is also some of the physical limits of the scale. In terms of like the bearings would start to get hot, you'd start to damage the glass, the stresses would be high, like that sort of thing. But I just like working with the raw output, and when I saw that the scales just output this sine wave, I was like, oh, that's really not that hard to analyze and process, and we might as well just do that instead of basically making the same circuitry, but to ask the DRO 100 times a second for ASCII output of the current numbers that are displayed on the screen. I would rather have the raw information, and then we can build shit on top of this. So, will we make a CNC as well? Yeah, that's kind of what I'm thinking. I really don't want to buy CNC machines, but I would be interested in making CNC machines. Like, I just know that software ecosystem is going to suck big ass, and the entire space is probably going to be software restricted, limited, DRM, paywalled, only working with companies that are large enough, or like all sorts of shit. I just want to make this stuff. Like that. I mean, I'm interested in tool making, and making a CNC machine is tool making. I would like to get control of how heavy of a machine I make and what tolerances I want to make the machine to, and how tight of control axis I have and how much feedback I have. And I want to be able to get all of the raw sensor data, because I would imagine that most CNC machines allow you to use conventional tooling to program their software, but I'd imagine other than literally the UI and maybe like 100 megabit Ethernet controller and an ASCII protocol, you probably don't get much raw information from them. You probably are just more able to send it operations like G-code to just perform for you. There's some open source projects. Obviously, I have no interest in open source projects. I'm not going to look at them. I'm not going to build off them. I don't give a shit. Sorry. I just don't care. The open source software is going to be equally shit. In fact, it's probably going to be way worse. Don't get me wrong. That doesn't mean that it's not good projects. I just know that the open source software is going to be probably mainly designed around low-cost 3D printing, which is a completely different project space. And it's probably going to be built around people who don't really care about working with greasy and oily machines in a dirty room where you want things to be nicely enclosed and clean and whatever. Like, obviously, there are people who do conversions of really nice machining tools to make them CNC, and they do open source stuff. Come on, open source software sucks. We know that. This is such high quality content. Hell yeah, thank you so much for the 4 months. Mucinex. Musinaub. How does it go from the 2 sine waves to the 0.1 micrometer resolution? I am very convinced in my head that the only way that that can be done is through the voltage. Basically, where are we on the signal, right? Are we high? Are we low? Are we at negative 10 millivolts? Whatever. So that works if and only if you know exactly that the peak is plus 1 volt, the trough is minus 1 volt, then you should be able to sample this and know from the crossings in these 2 phases, you can determine the direction that the scale is going. And you can know like where you are for each of the sine waves, and then you can interpolate your position in that sine wave based on the voltage. And that's it. So my scales and my DRO allows me to go to 0.1 micrometers with that's a 200x sampling, and that's because take 20 micrometers, divide it by 200, and that is 0.1. That is how they do it. So when you're in the DRO, you have to go into the settings and like change the divisor or multiplier or whatever they call it to 200. And I assume that's just how it's binning the ADCs or something like that. I don't know how else you could do that. I genuinely do not know how else you could do that. There's, to my mind, you could potentially go down to 5 micrometers without an ADC or without like more than a comparator if it is safe to rely on the fact that the sensors, the two different phases are truly 90 degrees apart, or at least close enough to 90 degrees such that they're closer than the resolution that you're trying to get from the scale. In which case, you could go down to 5 micrometers because with 2 waves, you have 4 crossings per, right? And they're all equally 5 micrometers spaced apart. That is kind of what I intend to use. I kind of plan on using that property. My plan is to determine which 5 micrometer bucket I am using very, very crude digital crossings that have much higher... Basically, I plan on relying on either the 20 micrometer or 5 micrometer, like these very, very obvious crossings where it's the sharpest signal increase. It's the like... It's basically the highest derivative of the highest slope of the sine wave is going to be at that crossing point, which means that that is just the easiest place to detect and maintain a count. So effectively, I'm going to have like a digital style mechanism that's going to tell me which 20 micrometer or 10 micrometer or 5 micrometer bucket I am based on those crossings. And then within that, I am going to make a determination of where we are within that 20 micrometer window based on the voltage of the signal. More specifically, my plan is to, based on where I am in that, in the like 5 micrometer windows, I can actually pick the phase that will be closest to an intersect, a Y like crossing the y-axis, the x-axis in this case, crossing the x-axis such that I can pick the sine wave that has the highest amount of signal to noise ratio, aka pick which one is not at the peak, but which is at this crossing point, once again, because of that slope. My view in my head, I don't know if this is a common signal processing thing, but like the logical gut feeling in my head is that my ADCs are going to perform better and be less susceptible to noise when the voltage swings that I'm trying to detect are larger. So I want to pick whichever waveform is closer to that point. With these both being 90 degrees apart, there will always be one that is very close to an intersection, or at least there's... Basically, one is going to have a higher slope than the other at all times. Does that make sense? So that's basically my theory here and why I plan on doing this. So, basically I want to extract as much digital information that I can as possible because I think that will be easier to maintain. That is how I'm going to like maintain absolute positioning. And then anything under that is just going to be through the ADCs. I honestly don't get the slope thing. Okay. So, okay. Plot sine x, right? Here's a sine wave. Set samples 1000, set grid, replot. Okay. So, this is a sine wave. There you go. Congratulations. Now, with respect to time, so let's say the x-axis is time. When you are up at this peak here, this is, like, when you go through this peak, you actually hit a slope of 0, right? At the very top of here, you transition from the going up to going down, which means you technically cross through 0, where you are actually no longer making any change. Now, the thing is that this slope is basically decreasing. The slope's getting lower and lower and lower, and then hits 0 at the very, very top of the wave, and then it starts increasing or decreasing, however you want to look at it, or what side of the wave you're looking at. Now, due to this, that means that the slope is decreasing slower and slower and slower and slower. It hits 0, and then it increases more and more and more and more and more, and the slopes get steeper. Now, what this means for me is that when I am looking at this sine wave, and I'm working with an ADC, the ADC is trying to determine the voltage of this sine wave, right? And the ADC is going to do that by bucketing the analog voltage into a bunch of different digital buckets to tell me where it is. So, like, if you have an 8-bit ADC, you are going to quantize this into 256 discrete Y values. And if you think about that, the Y values are going to be very, very, very close to each other up at those peaks, because you're basically, the voltage is effectively not changing during that window. The derivative is 0, yes. ACOS is less precise when it's at the peak. This is because the derivative of cosine peak is at 0, so the derivative of ACOS is infinite, so it has bad precision. All that makes mathematical sense. Yeah, really what this comes down to is that this is going to get chopped up into discrete components. So let's imagine that the ADC outputs literally where this grid is. So you see where the grid is. I don't know why my GNU plot doesn't show my cursor. It's really annoying. It doesn't show it for me either. I'm completely blind here. So imagine that each of these grid lines, right? See these grid lines? Imagine that the ADC can only digitize to these buckets. Now that means that this entire peak here, this entire area, would be the same value, right? The ADC would see this entire selected window as one value. It crosses over that threshold, it gets put in this new bucket. This entire time, this is just one value. I have no way of discerning what the values are in this entire window. That is the resolution I have. Now, what's nice is that when we're looking when the derivative, when the slope is the highest down here, that window looks more like this. Obviously, the height of that window is the same. The y-axis bucketing of the ADC is the same, but the window width, the time period which it sits in that window, is much smaller. So if you imagine that I'm moving the scale and we are moving through the sine wave, and that's time, it means that we sit in that bucket for the shortest amount of time, which means that we will go to the next bucket and thus have more information, know that we can step to the next bin, that sort of thing, sooner. Now, in my case, my ADC is 13 bits, so if you imagine we chop this up, it's actually in many, many, many components. It's in 8,192 components compared to the 10 that we're simulating here. But the same property and same effect still exists. There's just more movement of the voltage that we're measuring. There's more ability for that voltage to transition between points of noise, right? So wouldn't you double your precision if you used a bridge rectifier? As long as you're not clipping. I mean, I'm going to get both sides of this sine wave, right? So I already get that. You could amplify the signal, but then you're going to be adding distortion from the amplifier itself. So my view is I want literally the direct fucking output of the scales, because that is what is calibrated. That is what actually from the factory is meant to have a specific meaning, and I just want to jam that into an ADC. I don't want to do analog filtering or anything like that, because that could distort the voltages, the waveform, those sorts of things. So, yeah, that's effectively what we want to do. Okay. I also don't know what these scales output. I don't know how much power they output. I don't know how much putting an amplifier would affect the output. I don't know if they're expecting to go into high impedance, if they're expected to go into a transistor. I'm not 100% sure. I don't think it's specified what their milliamp output is. I don't know what the distortion, those sorts of properties are. Thus, I'm just putting them into the ADCs right now, literally directly from the pinout. In reality, I think I might just want to put a 1K ohm or 1 meg ohm resistor. I don't know what the impedance is of my ADC. I can just check in the spec. Because in theory, if the ADC is low impedance, it could potentially draw a lot on that input and affect the input. But I think the whole point of an ADC is to be high impedance. Okay, so we need to talk to the ADC. I decided to get a 13-bit ADC, and the reason for this is this is basically the highest resolution, the highest y-axis resolution, the highest voltage resolution, 13 bits, is effectively the highest that you can get in a DIP package, a dual inline package, which is something you can just put on a breadboard, so I can do that during testing and initial stuff. And you can just jam it on a breadboard, and this samples at 100 kilosamples a second. So I'm able to supply this with 5 volts. This is a differential input, so this takes not just one input and ADs it. This actually takes in an input positive and an input negative, which is really nice because I can put in the sine wave input to this, and then the reference voltage, that 2.5 volts that the scale gives me, as the in minus, and now I actually digitize a waveform that goes positive, negative, positive, negative, positive, negative. So I really, really liked this chip. All the things that I looked into, it's just really nice. 100 kilosamples a second should be enough to handle these scales at their maximum travel of 2 meters a second. In reality, the fastest that I can actually move my scales, I had some good notes, but I probably removed them. The fastest that I can move these scales, I think, is 1,000 millimeters a minute. which is a meter a minute. So effectively, I would like to design this software such that it could be used at the limits of the specification of the scales, that 2 meters a second, which requires being able to keep count when that sine wave is 100 kilohertz, right? And 100 kilosamples a second might not be enough. If we have to drop the specs a little bit, that's fine. In reality, I care more about the precision, but I think I could at least grab a 200 kilosample chip and put it in and just redefine some parameters. Basically, I want to make this whole project pretty ADC agnostic, because I could see people using this, because these scales are cheap. I mean, they're like $1,000 a piece, but that's pretty cheap for the quality of the scale. And the DRO is expensive. It's like $1,000 for what? 3 fucking 8-segment displays. And I'm pretty sure that like DRO has not changed for like 30 years. They made it. It works good enough. It's fine. But I could see like open source and home shop people enjoying being able to control these scales directly. And I don't know, I think this is a really good introductory project to FPGAs, which I've worked with FPGAs before, but so little that I effectively don't know anything about them. So, okay, so these are the ADCs we got. We have to communicate with these ADCs, obviously, because we need to get the information out of them. I actually already set up a circuit that can communicate with them. It's trash, though. So let's talk through what pins we need to operate this ADC, and like how do we actually drive this? How do we get our signal? So we have a VREF here. This is the reference voltage. This reference voltage is the highest and the lowest values that can be output by the ADC. This effectively determines your vertical resolution. So if you put in a VREF of 5 volts, then you are able to supply plus 5 volts and minus 5 volts, and all Fs, like the int max will be VREF positive, and negative int max will be VREF negative. So VREF is actually a reference point. It is telling you it is effectively determining how you convert the bits into an actual voltage, right? The highest position is positive VREF, negative VREF is negative. So, that is the reference voltage. That is your high and low points. The input plus, this is the positive input. This is the negative input, and the ADC is going to effectively subtract these. It's going to do in positive minus in negative, and it is going to tell you the digital representation of that with respect to this reference voltage. You have VSS, this is just grounded, this is just the low voltage for the circuit. VDD, this is the digital, this controls like the digital, this is the power for the chip, so this is 5 volts. You have the clock, this is actually what is used to sample the serial output. Digital output, that's the literal output, this is where I get the bits from. And then you have an inverted chip select or shutdown. Basically, this determines whether or not the chip is operating. Obviously, the chip is going to go into like a low power mode, and the spec will actually define that when you have this pulled high, when chip select is high, the chip is shut down. Even though it's powered, it's going to draw a very, very, very small amount of current. So this is a very, very simple ADC. The reason that this is so simple is because this actually doesn't have any inputs or addressing. So most ADCs that you're going to encounter when you're like fucking around with ADCs are going to be multi-channel ADCs. And the way those will work is you'll have another pin, a D-in pin, and you will use the D-in pin to address which channel you want to sample. And you can only sample one at a time, and effectively you're going to clock in, like, hey, I want to get the voltage of channel 7, and you clock in 111 to clock in 7, and then you maybe clock a couple times for it to actually sample it, and then you clock out to get the output. This one only has 1, so we don't even have to think about that. This is literally only output. So the only thing that we have to do to control this is, and the what's happening with the webcam? What's wrong with it? It looks fine. Looks fine to me. Was it just shaking? Is that it? Because I was moving my position in the desk. It's probably just shaking. Okay. The way that I have set this up is I have VDD set to 5 volts. I have VSS set to ground. These are being supplied directly by my FPGA. So my FPGA GPIO headers give me, I have all of my GPIOs. I then have a 5-volt supply. I have 2 grounds and a 3.3 volt supply. And I am able to drive these scales directly off the FPGA. These scales have a very, very, very simple circuit in the head. I'm pretty sure all it's doing is just basically taking the 5-volt supply, applying that to an LED. That LED is shining through the scale, and then there is a receiver diode, a photodiode, that is then directly sending me the data out. That's effectively all that's happening. There's a potentiometer on the reader head that affects the voltage I get out. Due to the way that the voltage clips and behaves, I am inclined to believe that I think that is not actually affecting like an op-amp or an amplifier of the signal. I think it is actually affecting the intensity of the LED. That is my interpretation. I haven't reversed out the circuit. I don't know exactly how it works. But there's a potentiometer that allows me to change the voltage output that I get from that 1 volt peak to peak to whatever the fuck I want it to be until it starts clipping and saturating. Yeah, it could be an amplifier. I think it is the voltage for the diode because it just cuts off. When you drop below like 500 millivolts, it just completely cuts off. You get no signal. You're completely in the dark. That kind of makes sense to me for a diode. That doesn't make, for an LED, it doesn't make as much sense for an op-amp to cut off at such high of a voltage, in that case 500 millivolts. To me, that's too high of a voltage, I think, for the signal to just literally disappear. This is probably amplifiers before you get the signal out. Yeah, I'm not 100%. There probably have to be, because obviously the direct photodiode is going to be way too inflexible. So yeah. There will definitely be like at least a buffer or something on the way out. Okay. So I supply, due to the FPGA pinout I have, I supply 5 volt to the scale. That's what the scale's supposed to get. I give the scale 0 volts, ground. Then I give this chip 5 volts at VDD. I give ground at VSS. Now I've supplied power to the chip. The chip is capable of operating. I supply right now, I supply 3.3 volts to VREF. I have basically 3 voltage supplies. I have a 5 volt supply, I have a 3.3 volt supply, and I also have the 2.5 volt supply from the scale. That is the reference point for the sine wave. I just put the 3.3 on it just so I don't saturate the ADC scale right now, because the digital wave, or the sine wave, will clip at the 5 volt boundaries, right? I don't think there's anything in this circuit that's capable of doing voltage multiplication, so I'm pretty sure that at 0 volts, I will get 0 volts regardless of if the sine wave wants to go further with the setting on the pot, and it will clip at 5 volts, right? So I'm going to clip to plus 5 volts or ground. the signal is based around 2.5. So in theory, I should be able to put vref as 2.5 as well. Right now, I have it set to 3.3, which allows me to go up to 2.5 plus 3.3 volts minus 3.3 volts, which in reality exceeds the range that I think I could ever get from the scale, because I think the scale is just going to be clipped at plus 5 volts or 0. Anyways, I just have that set to 3.3 volts. It just means that I won't fully saturate the ADC yet, which is just nice for experimentation and testing. I will probably eventually just set that to the 2.5 volts because you want to use the lowest reference, right? Because the reference is stretching that scale out. So if you have a reference of 10,000 volts and now you're digitizing with 13 bits, each bit is like 2 volts, right? So I want to have the lowest peaks there. Okay, so right now I have that 3.3 volts, but it'll probably become 2.5. In positive, this is the sine wave output. This is the reference from the scale. Then the clock, digital out, and chip select, these are the only pins that we need to drive from the FPGA. Everything else is hardwired to a supply rail or the actual scale. So there's only 3 pins that we have to worry about to communicate with this ADC. Okay, now this is a shift-based output. It has a serial output. That means that unlike a parallel output chip would have many, many pins, and you would effectively like get all 13 bits as all separate pins, and you would just like apply a clock, and you get all 13 pins being the actual digital output of your signal. In this case, it's serial. Most of these are serial. It's just smaller, more pins, more board space, more expensive. So what this does is it actually samples it samples the input, it keeps it in there, runs it through this comparator, and then has the shift register, which is just going to pump out the 13 bits each time you clock. So effectively, the way that I'm going to communicate with this is I'm going to tell the chip via chip select, I'm going to bring chip select down to basically say, hey, I want to use you, I'm ready to use you. Then I will apply clocks to basically, it will want like a couple clocks probably to sample, to hold it. And then eventually, according to its spec, it will then start clocking out the digital bits one at a time. So the first one will either be bit 0 or bit 13, bit 12, whatever. And you clock them out one at a time. So effectively, I'm going to keep asking the chip, thank you, I got the bit, give me the next one, 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 and you're just going to clock out all of those bits. Okay. Why do you need an FPGA? Because I want more real-time data. There's potentially just more risk of doing this in a microcontroller. Not really, in this case, since it's standard SPI. But I don't want to use a microcontroller. FPGAs are just better. Okay. So we can look at the specifications for this chip. We can see the maximum allowed input voltage is 7 volts to power the chip. We're giving it 5 volts, so we're within that limit. We're doing fine. All inputs and outputs with respect to VSS, this is basically saying how much can I put into like the analog input maximally, and that's up to VDD. So if I'm giving it 5 volts, the maximum I can put in is 5 volts, but that's the maximum I can get anyways, so that's fine. This can sample at 100 kilosamples a second. Now this chip is actually very interesting in that you can talk to this at this chip. This chip takes 16 cycles to operate. What's really cool about that is most SPI buses that are hooked up to a microcontroller are going to need to talk 8 bits at a time. So what's really cool about this is you can actually just do 2 8-bit words to this directly through like a microcontroller SPI bus and talk to it directly. It's really cool. Conversion time is 13 clock periods. So this is basically telling you how long it takes to, I guess, perform the entire conversion to convert the analog to digital. The no, I think that's the time just to clock it out. I'm not sure. I don't know what the conversion time is. I think that might be. The acquisition time is how long it takes to sample the input. This is basically how long it takes for it to like charge an internal capacitor that's going to sample and hold it. So effectively, this chip, when you like apply the first 1.5 clocks, is going to be saving the input, and then while you are clocking it out, I guess it's converting it into that digital output, and you're getting that information, right? So in terms of like how long do you need the input signal to be stable, that's also all specified in here. The resolution is 13 bits. It's 12 data bits plus a sign bit. So you get 13 bits of information. So we divide up this entire space into 8,192 discrete outputs. So in theory, if we can get our noise to 0, we could technically sample this down to 20 micron divided by 8192. In reality, that's not really going to be feasible. There's going to be too much noise. But I see no reason why we can't at least do a 200 times division like the existing DRO does. I imagine that this ADC is probably nicer than what they put in the DRO, just because this is an expensive part. This is probably like a $5 ADC, and they're just going to put a 10 penny ADC in because it's way cheaper. They probably have an 8-bit ADC, or they do just a completely different way of sampling this. I'm sure they go through a comparator before an ADC. We're going directly into an ADC because we can handle this in real time. Bunch of the accuracies, basically saying the nonlinearity and stuff. Basically, I think this is just meant to be plus minus 2 LSBs. So plus or minus 2 least significant bits is effectively just noise. So the bottom like 1 or 2 bits, there's effectively no information in them because the noise of the actual circuitry is going to be louder than that. However, in our case, our reference voltage is probably, I have a really nice multimeter. We can do metrology and try to determine how high quality our 5.5 volt supply is, our 3.3 volt supply, our 2.5 volt reference. I imagine the 2.5 volt reference is actually very nice. The 5 volt supply is probably meh because it's right off the FPGA, but it's probably okay. But that 2.5 volt reference has to go through a long 2-meter long cable, and there's grounding and interference stuff there. So ultimately, the noise of the chip is likely not going to be where the noise is going to be coming from. The noise is more likely going to be coming from the actual ability to get a good reference voltage with the way that, at least in this breadboard situation, there's like my hands moving around will affect it probably more than those 2 bits. It's a Japanese company, so they might have custom silicon just because they can. Yeah, they could. Yeah, I haven't taken apart the DRO. I don't want to. It's a little more expensive than I want to tear apart, even though I'm sure it's really simple. Okay. Anyways, we're all within the limits of everything in here. So, the things that we actually care about are how do we communicate with this? We know the high-level input voltage has to be over 0.7 volts. The low level has to be underneath 0.3 volts. That's super simple. That is completely within spec of like a standard 3.3 volt TTL. So I can drive this directly with my 3.3 volt TTL logic. High-level output voltage, this is saying that it's going to output, since I'm putting in 5 volts, I'm getting 4 volts out. I'm actually driving in, I'm probably driving in 5 volt into a 3.3 volt pin, which is probably okay, but it's something that in theory I should do a conversion of that. I can't, in this case, use 3.3 volt to supply the chip because that would cause clipping issues on the ADC. Right, I need the range to be plus minus 2.5 volts from a 2.5 volt center. So I need to supply 0 and 5 volts to this chip for the actual supply voltage. So if I wanted to change that digital level, which right now I'm just jamming it into the fucking GPIO because I just imagine there's enough protection on that pin to handle a 5 volt signal. It's probably fine. I don't know. You can get like TTL converters where you convert from like a 5 volt to a 3.3 volt. I don't really give a shit. It's fine. We can blow up a chip. It's totally fine. I'm not too worried about it. We can just, I got a bunch of them. We can put new chips in. We're not going to anyways. Okay, so what matters more to us are the clock frequencies. So we need to communicate with this chip, and there are timing specifications that are telling us our minimums and maximums. Now, obviously, these chips can be overclocked. As with anything, these minimums and maximums are going to be minimums and maximums where it must function fully correctly and properly. So we can just use these as our actual minimums and maximums. These aren't like the chip stops communicating below this. It's that it could, but in reality, they probably have some percentage buffer rooms on their end. So what I want to do is I want to write control circuitry that allows us to communicate with this ADC and maintains these timing specifications. I want to parameterize it such that I can give it an arbitrary clock frequency input, and we will synthesize a counter that will divide that clock down into whatever is necessary to drive this chip. And I want the Verilog to hopefully fail to compile if the clocks that we give cannot run this chip. And that's kind of what I want to experiment with. That's why I kind of got excited for streaming. And all of these timings, basically, I want to put all of these timings into constants in Verilog, and then I want to, based on the input parameters for the clocks and whatever, I want to then also verify that we satisfy all of these timings, and then we're good. And then that allows us to potentially just change a constant, and now we're sampling this at a different speed, even though we're giving it the same clock, and that sort of shit, right? How does that sound? Does that sound fun? Really, we want to clock this as fast as possible, I think, because, let's look at the, somewhere it will talk about the current draw. Yeah, here we go. Okay. So this is telling us the current draw, basically the efficiency of the chip. So this is saying that 5 volt input, it's going to draw typically 300 microamps when the voltage reference is 5 volts, and when the voltage reference is 2.7 volts, about 200 microamps, and up to 450 microamps. But when the chip select is high, right, when we're basically saying we're not using it, it drops down to 0.05 microamps, so 50 picoamps. So what this tells me is that I actually want to clock and operate the ADC at the highest possible speeds. If I want to sample at a slower speed, then I would rather just basically have the chip off, right? If I want to sample this 1 time a second, I want to sample it at the maximum speed, but with a lot of downtime, right? Because it will consume less power. I mean, this is ridiculously low amounts of current, which is actually nice. Now, since I'm using a dev board, current draw just doesn't matter, because with a dev board, you have so many peripherals drawing fucking power that, like, doesn't matter. Although, in theory, most of the peripherals on, like, an FPGA dev board will be in this, like, low-power standby shutdown state. Hopefully you need to drive them to actually activate those chips. But I think we want to run it at the highest speed. That could depend on if there are any benefits to the quality of the signal if you sample it slower. Effectively, if you clock it slower, do you allow that, like, capacitor, do you allow this sample and hold circuit to sample at a higher precision if you clock it slower, at least for that acquisition window. Like maybe for these 1.5 cycles, sampling slower improves that quality, but I don't think so. We'll go and try and check out some graphs and see if they specify something like that. Oh, here you go. Sample capacitor is 25 picofarads. And I imagine that if it talks about that, it'll probably talk about, like, the charge up time and stuff for that. Okay. I don't think gating power to user built peripherals, but I never looked at it. So FPGA, like, if I want to talk to the ADC that is built into the FPGA dev board, I have to do the same thing that I'm doing here, and it has a chip select and shutdown, and that will... Maybe that will be 0. I'm not 100% sure, but in theory, you have control of those same pins. So in theory, I don't know if I would have to actually drive that pin high, or if it has an inverter built in, or they used a chip that has a low shutdown. I'm not 100% sure. But in theory, I could probably power down many of those peripherals by driving those shutdown pins on all of those, but I'm not gonna do that. I don't fucking care. Okay, perfect. Here we go. The very first graph, this is, unless otherwise specified, voltage, supply voltage is 5 volts and reference voltage is 5 volts, and 100 kilosamples a second, and you're clocking it at the 17 times the sample rate, so you're sampling it at exactly what's necessary. Okay, so effectively what this graph is telling me, I don't know what the INL is, negative and positive INL. This is in least significant bits. Input loss, maybe? I don't know. Effectively what this is telling me is that it literally doesn't matter how fast you sample it. In fact, it looks like the faster you sample it, the better the quality is. That is my interpretation of this graph, is that the INL, which I imagine is bad, I imagine you want lower INL, nonlinearity. The nonlinearity goes down, which I imagine is a good thing as I sample. Okay. With temperature... Unless it's bad. Maybe it's bad. I don't know. I don't actually know what non-linearity means. Voltage reference. So it looks like you want... I imagine it's good. I imagine it gets better because this graph gets really bad when you give it a really low reference voltage, which would make sense. This probably asymptotically approaches infinity. Ideal transfer function of a DAC or ADC is a straight line. Yeah, non-linearity. That's basically saying, like, basically when it quantizes it, you want it to quantize it perfectly linear, where 0 volts and 5 volts, it's a straight line. Like, all of the bits perfectly encode that as a straight line. And yeah, that's just the non-linearity of it. Deviation between that. Yep. So yeah, it looks like it performs better the faster you sample it. It looks like it also performs better the higher the reference voltage, but maybe it's the best around this like 3.3 volts or 2.5 volts, which is actually what we're using as reference. Differential non-linearity, pretty much a straight line there. This is the non-linearity versus the code. So this is a really cool graph. So this is telling you these are the different digital outputs, right? So you have negative 4K bit and positive 4K bit. This is telling you basically like where you experience that non-linearity. And you can see that there's kind of a positive component here, or like a negative component here and a positive component here. I imagine that these are like similar components of the circuitry. So these areas are technically like the worst areas for this non-linearity, which makes sense. Like everything is analog at the end of the day, and this repeating pattern just probably has to do with fundamentally like how their circuitry is designed. So what's really, really crazy is that like I could, in theory, like build this graph for my specific ADC, and I could probably get way, way, way more information because I would effectively be calibrating my ADC. I could also store this graph in ROM and perform compensation for it. And like those are the sorts of things that I'm really interested in doing that kind of require like you can't build stuff with off-the-shelf parts to that spec. Obviously, you have to build them within the spec of their specs. This spec is telling me what I can rely on out of the box. What I like doing is figuring out my specific chip, not the model number, but literally the individual physical chip that I have in my hand, measuring the performance of that and like really, really getting more information out of it. Differential versus reference. It's kind of a low spot in this 2.5 volt. Once again, all of these graphs are telling me that like my error is going to come from elsewhere. So like I just don't care about any of this error. Temperature error has an effect. Positive gain error has a little effect on it. Input frequency. So this is saying that the signal to noise ratio gets worse. Signal to noise ratio has this like dip here, some attenuation at the like 10, 20, 25 kilohertz range. Reference voltage looks like you need to have a certain amount of reference voltage for it to function correctly, which is fine. We're never going to go under 2.5. We look fine on that graph. Harmonic distortion, all those sorts of things. Signal noise. Oh, yeah. I think the easiest one for us is effective number of bits, this ENOB. This is the root mean square effective number of bits. So 13 bits is how many bits it's giving me, but how many of those bits actually contain information. This is saying that as long as the reference voltage is above like 2 volts, I'm getting like 12.5 bits of actual information out of it, which is pretty damn nice. So I think ultimately I'm really happy with like how many graphs they have. I like this chip. It's nice. Okay. So this is how you determine the LSB size. So this is basically the size of a bit. 2 times voltage reference divided by 8,192. That's because 8,192 is 2 to the 13th power. That's 13 bits. You have plus minus of VREF. So the full range is positive VREF to negative VREF. So you have 2 VREF ranges. So 2 times VREF divided by 8,192 tells you the step size, like how, like when you get 1 more bit, when the counter goes up by 1, that is the voltage increase, right? I trust the ADC is fine. Yeah. So anyways, we need to control this chip. Okay, so this is the timing parameters for the chip. So there are some other graphs, I think, other digital graphs that like describe communicating with the chip. But they don't talk about it as timing parameters. Oh yeah, here's like the graph kind of describing like VREF, negative VREF. You can encode negative VREF, but you can't encode positive VREF. In this case, positive has 1 fewer bit because 0 takes away from positive, right? Right, 2's complement. Why this chip in particular? It's 13 bits, it's a DIP, it has a good spec, and it runs at 100 kilosamples a second. It's the highest resolution ADC you can get in a DIP package that is also at 100 kilosamples. You can get 32-bit ADCs, but shit, even at 13 bits, like your ground plane and like doing this on a breadboard, there's going to be noise from the capacitance of the like solderless connections and shit that are going to be way, 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 way worse. 32-bit ADCs probably require like a proper multi-layer PCB with like a separate analog and digital ground planes and like proper physical isolation of components. So anyways, this is effectively how you operate it. So I don't care about this LSB first format. This is the only way that we're gonna clock it. So effectively, we pull. Dude, this microphone is driving me nuts. Effectively, we pull the chip select low, and pulling that low activates the chip. We're basically turning the chip on. Remember that when that's high, it's using basically no power. So we pull this down. We then clock it. And first we clock it to basically cause the circuitry to do acquisition. It looks like you have 1, 2, 3 clocks that do nothing. You technically get a null bit out, but that's not information. So 1, 2, 3 clocks. Then the next clock, you get the sign bit, and then bit 11, 10, 9, 8, 7, all the way down to 0. And then once you have gotten 0, the last bit, you can return chip select high. That shuts the chip down. And that's it. That was the sample. This is all we have to do. We just have to run a clock. We have to pull chip select down. We have to run a clock. We have to know that 1, 2, 3, 4. On the 4th clock is when we start getting data. And that should make sense because there should be 13 or like 12 bits. 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yeah, there's 16 clocks for the entire process. So pull this down, 16 clocks. The last 12 clocks are the ones that actually allow me to have the data, and that's cool. Okay. So, what we want to do is we want to actually look at the analog circuit timing parameters. So the other one was kind of showing like a high-level overview of how you actually operate the chip. This one is telling us the actual timing properties of like how quickly after pulling down the chip select can you issue a clock. How long is it until a clock pulse and being able to read data? How long do you have to keep the clock high versus low? How long until you can disable the chip before you lose information? So this is the very, very, very simple waveform that we are going to be designing a circuit to process, and I want to do it quite well. I want to like try to accurately model this waveform and effectively tell you if the input clocks that you're giving the circuitry do not allow us to satisfy any of these timing properties, and if they don't, I want it to fail to compile. That's what I want to do. So we're going to be doing some Verilog. I'm going to go, fuck. It's going to make waffles, but I don't have toppings. I'll have to do syrup. I don't have any peanut butter. So I'm going to go make some Eggos because I'm hungry. But yeah, this is what we're going to be working on. What happened to the OS fuzzing with AVX 512? I mean, I still have that, like the vectorized emulation stuff. I still have that. I still use it every once in a while, but not very often. Okay. Okay, so I'm gonna go make those Eggos. Give me a few minutes. Feel free to chat with yourselves. Be right back. It also says the stream is unstable. Am I dropping frames? Not really. I've dropped like 33 out of 500,000. I think that's totally fine. Be right back. Hi, Gloomis. You having a good nap? Yeah. Okay. Alright. What's chat been doing? And now we eat. Tell me about your day, chat. Do you have dreams where you find dead animals? Dead animals in your house? No. Never heard of that. I'm trying to figure out MLIR. Good luck. I refactored some C#. And now I'm going to write more C#. Shout out to C# fans. Okay. What dreams you got? Just fucking random. Usually like what I did the other day. Dude, waffles are good for your health. How big is the environment for this FPGA? What do you mean? Yeah, so I think we're just gonna process this this data left to right. So the first thing that we really care about is this T sucks, which is 100 nanoseconds. Clocks chip select fall to first rising clock edge. So this is basically saying how long we need to wait to clock the chip after dropping chip select. So once we turn on the chip, how long until we can start clocking it? And that's the first thing we want to determine. We want to figure out, we want to drop that chip select down and sample it. That should be pretty easy. I already actually built a circuit that can drive it. This Verilog can sample it and display it to the LED. It's shittily written. I'm sure there's like issues and maybe edge issues. Honestly, this is probably actually totally fine. Let's see. I drown my waffles in the syrup. Yeah, I use a pretty light amount of syrup. I've never been a huge syrup fan. Normally, I'd do peanut butter instead. Anything else in here that's interesting? I wonder when this chip came out. Buffering them. If the source is not low impedance. I do like this chip. I think it's a pretty good spec. In the grand scheme of specs I've looked at, I feel like it's a pretty nice spec. Is there a revision history? Nope. Yep. 2001, original release. I got the B grade, I think. The higher grade. I got the plus minus 1 bit. Why would I get the plus minus 2 bits? Are you still self-employed? Yeah, I'm fun employed. Hmm. Hmm. MCU latches data on rising edges. It's clocked out on falling. Yeah, this is like directly powering it from a microcontroller, which is just really cool. Just two 8-bit pulses, and you can sample it. I imagine that's why it's 13 bits and not 12. Hi, Smumbus. Hi, Bubble. Hi. 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 Little boy. Are you getting up? Then I gotta play with you. If you're getting up, I gotta play with you. Hi. Hi, Bubble. You having a good nap? Yeah. Yeah. Hi. Who's a good boy? Who's a good boy? Yeah. You like your hedgehog? You like your hedgehog? Yeah, is your hedgehog good? Is your hedgehog good? Here, let's make you full screen first. Yeah, I'm just a second, S'mores. Just a second. This'll do. Yeah, who's a good boy? Who's a good boy? I like your hedgehog, S'mores. That's a very cool hedgehog. Yeah. Who's a good boy? Who's a good boy? Did you know you have the groomer coming today for you, S'mores? Yeah. Yeah. Hi. 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 You want a tunnel? You want a tunnel? You want a tunnel? You want a... Who's a good boy? Who's a good boy? Who's a good boy? Who's a good boy? Yeah, you're a good boy. You're a good boy. Can you sit? Can you sit? Sit. Shake. No, that's lay down. Okay. You're a good boy, though. You're a good boy. Not the brightest. You want a kiss? Good boy. Okay. What font do you use? I think it's Terminus. I don't know. They're all the same. Okay. How do you find contracts to work on? Do you just get contacted? Yeah. I've never applied for a contract. Seems like a super normal data sheet. Yeah, I mean, it's pretty normal. really is it's not bad, is what I'm saying. Okay. All right, what's next, chat? You ready to write some code? Okay, so this is the code that I wrote before. Super simple. So I have a 50 megahertz clock from the FPGA. And then what I do is the chip select. Basically, I divide it down. I just have a counter, the sequence counter. And I just divide it down so the bottom bit is the clock that I drive this at. I forget what speed I picked, something slow as shit. I think it's this 98 kilohertz. And then the other bits, let's see. Yeah, the bottom bit is the clock, and then the bottom bit is the clock. Or wait, no. The bottom bit is the clock, and then like 4 or 5 bits up is the chip select. 4 bits up, right? So this means that I have the chip enabled for 16 cycles or 32 cycles. I forget what I did. I'm like oversampling. I think it's just 16. So basically, I turn on the chip, I clock 16 times, I turn off the chip. I don't really like this. It's kind of shittily done. I mean, this is fine. This is probably just like normally what you'd do. But I'm kind of curious, like, how nice we can make this. Like, how much control do we have in Verilog to make this not absolute shit? So what we need to do is we need to define all of these timings for our waveform. And I think, yeah, we want to clock it at the highest speed, is my view. So I think my view is we want to pull chip select down, wait T sucks, and then fucking clock 16 times as fast as we possibly can, according to T high and T low. And then we want to go from there. So the ASIC itself, I imagine that they are going to be sampling the data or shifting the bit on the down slope of the clock, on the falling edge of the clock. So we don't have to worry about that. I think on the upstroke of the clock, we will be able to get our data. So we need to pull CS down, we need to clock 16 times, and then we need to raise CS. That's all we gotta do. How much are you paid for this project? $0. Okay. Okay. Let's see. I'm gonna change up the music. I don't want Evanescence. What do we want? What do we want? Let's do some of this. Okay. That bass line's so good. Let's see. There we go. Are you planning to test this? Just in simulation. We're gonna just write simulation for this. Should be pretty easy. Okay, so let's see if we can just copy and paste this code and get it running in our test bench. Or at least very similar to it. So I'm trying to do more of this in Vim now. I was playing around with these specify blocks, so we got some shit in here we don't need. Oh god, is that really copying fucking is this seriously copying carriage returns when I copy this? Are you fucking serious? What is this? What is this boomer ass fucking Jesus Christ? Oh my god. Okay, okay. So basically, the way that you actually do everything in fucking Verilog is you do simulations. And the way that you do simulations is you make, like, a test bench that is, like, kind of like how you hook everything up into it. And then you drive it, and you see how it behaves. So the simulators are pretty accurate. Obviously, like, rise and fall times are more complex, but we don't have to think about rise and fall times. There's literally nothing in here that isn't going to be rising or falling fast enough. So all we have to worry about is just purely the digital logic. We can treat it as perfect square waves effectively. Okay, so let's make this a what is this chip called? MCP 3301. MCP 3301. So this is a driver for 13-bit differential SPI MCP 3301 ADC. Okay. So, initial begin. So this initial block is like where we can initialize things for the simulator, right? So this initial block is more like writing normal code, where we can like actually do logic and like initialize registers and values. This always at positive edge clock is when we can do logic on that positive edge of that input clock, and the input clock is supplied by the user of this module, right? So this is kind of like a function. It's kind of not, because it's like not executed sequentially like you'd expect. But at the positive edge of the clock, this happens. So in reality, this is going to synthesize down to like gates and flip-flops, so they're latching when that positive edge of clocks hits. So that's like when things get saved, right? This is what drives those like flip-flops and memory and RAM and timings and all that shit. Okay, so we're gonna have an input for S'mores, you wanna go out, Bubble? Let me let S'mores out. You wanna go out, Bubbles? Or are you just looking? You wanna go out? Yeah, you can catch up. Go on. Go feed him. Go feed him. Go feed him, S'mores. Good boy. Good boy, S'mores. What a good boy. What a good boy. Okay. Yeah. Yeah. Good boy. Okay, we have the clock input, we have the data input, which is going to be the data line. And then we have the output, which is going to be 13 bits. That's how this is going to work. And we'll probably want to have like an output clock that's like data ready or something, so that we can basically get informed when our data is ready. That would be my guess. Okay, this is... okay, so what I want to do is I want to make parameters, which I think is parameter, clock hertz. And we're not going to specify a default value, and this is going to be the input frequency in hertz for clock. the clock input. The frequency in hertz for the clock input. So what I want to do is, in our case, let's say it's 50 megahertz. Concerned about where you're going with this? Uh-oh. What am I doing wrong? So then, from my end, we're going to generate a test wave. Clock is going to be clock. Wave is going to be wave. We can just set that to 0. Generate a 50 megahertz clock with a 50% duty cycle. Okay, so basically this is just inverting clock. So we the initial state is we 0 the clock and we set the wave to 1, and then every 10 nanoseconds, every 10 nanoseconds, we invert the clock, which should generate a 1 over 10 nanosecond, sorry, 1 over 20 nanoseconds is the period. That is 50 megahertz, correct. So this is going to, in simulation, remember, this test bench is the simulation. The MCP3301 is actually what we'll be using to communicate with the actual chip, but we're basically just setting up test waveforms initially here. So we say that our clock frequency is 50 megahertz, because it is, and initialize these values. Then this is saying that we want to basically run the simulation for four clocks, for 4 positive edges of the clock, and then this is stop the testing, and I think I just have it to run all. Yes, so this will run until we get to finish, and I should just be able to run it. No instance DRO, correct. This is a MCP3301. Okay, so this port wave, oh, yep, data is, let's just say data instead of wave. Data Q is the output. Okay, we made it to finish. Sweet, and we got to the end at 70 nanoseconds, which, yeah, that makes sense. That is 70 nanoseconds is that 4th rising clock pulse, because it's on, it goes high. It starts at 0, so it's low. It goes high at 10 nanoseconds, and then it goes high again at 30, then 50, then 70 is the last time it clocks high, and then that's the end of the simulation. So effectively, we have a very, very simple little dev environment here where we can do this testing. So now we can write stuff that drives the lines high and low, and just drive it here and see what happens. Okay. So what I want to do is what I'm thinking is, you ready to come in, S'mores? I'll give you some time. Why Verilog and why not languages or libraries that compile to Verilog? I don't know, just because this is like more the fundamental building block, in my opinion. Okay, T sucks. So I need to... T sucks. How big is that? 100 nanoseconds. The fastest that you can clock is note 8. For slow sample rates, maintaining a minimum clock speed. Yes, yeah, you need a minimum clock speed. So I think I want to just drive it at the 1.7. Basically, I could require that you just pass in a 1.7, and then we don't have to do all this logic. Because 1.7, what's the 1.7 megahertz? 1 over 1.7 megahertz as nanoseconds is 588 nanoseconds. What are you going to do with that clock speed parameter? I would just generate a fucking counter. Let's see. 580. 588. Disable time is 580. But we have 588 nanoseconds. I mean, honestly, like, this is just so fucking easy to drive. Minimum CSH. Oh, okay, that is saying that the so you have to have the chip disabled for at least 580 nanoseconds, but at 1.7 megahertz, that's actually 588 nanoseconds. So in theory, I don't think any of these timing properties matter if you're using a 1.7 megahertz clock. I genuinely, like, none of these are high enough that you actually care. Yeah, but that's not what I want to do. I want to make this extra zesty. Is what I want to do. Let's try and zest it up, chat. We can talk to this real easy. Let's zest it up. I want to run this chip as close to its limits as I possibly can. How does that sound? How does that sound? So I want to drop CS to enable the chip, and then I want to 100 nanoseconds later, I want to issue that fucking rising clock. I think that sounds really fun, right? So instead, like, the way that you would do this, I would imagine, I'm not a hardware person, I imagine the way you would do this is you're just going to pick one clock rate, you're going to pick this 1.7, you're going to see that everything times out completely fine in 1.7, and you're just going to pull CS down, you're going to tick 16 times, you're going to save the bottom 13 as the 13 bits, you're going to drive CS high, everything's going to be based on just that clock at that clock speed. What I want to do is I want to take in a higher frequency clock than 1.7. I want to issue that rising clock edge 100 nanoseconds after, and then I want to, like, and then I want to sample it at the fastest speed with, like, the T high and T low. This sounds really fun. Doesn't that let me drive it faster than 100 kilosamples a second? Right? Because like can I make like the first couple clocks fast? Or maybe not. T high and T low. T high and T low. What's my limits? At 5 volts. Ooh, 275. 275. Okay, there's probably nothing we can do here. 275, 1/275 nanoseconds. 1/275 times 2 nanoseconds is the square wave, and that's megahertz. 1.81 megahertz. Okay, so the clock. Yeah, I guess I think the only place where I can shave off time is if the clock is low, I can shift ahead this start point, I think, is all I can do. I think that's literally all I can do. because the clock, high and low, the fastest I can run this clock is 1.81 megahertz according to the clock high and low. So, the only thing that I could potentially move forward is assuming that the clock stays low until I switch CS, I could potentially shift this clock up such that we're just T sucks away. Which in theory would save us, I think, like 200 nanoseconds. I think 200 nanoseconds is all we can remove from this. But I think, according to these timing parameters, we could remove those 200 nanoseconds and slightly get that. But there's obviously no reason. What sampling frequency? I'm just going to run it at max speed, obviously. Okay. Oh, I thought we could get cheeky. That would have been so fun. But there's just no reason to do that. High impedance on the output. TN. So this is the falling edge of the second clock. 1, 2. That's the time until... we get the first null bit. TN. 125 nanoseconds. TDO. T data out. Yeah. Clock fall to output enable. Clock fall to output data valid. Yeah, 125 nanoseconds. As a hardware engineer, I'd run that 1 megahertz if it's enough. It's not quite enough. I mean, it probably is for this, to be honest. But I'm probably gonna run it at max speed. I don't think it really matters for me. I haven't looked into my PLL yet on this. Where is my PLL? Let's see. PLLs. I think this is the one I use. Okay. Loading Mega Wizard. Reference clock. This is gonna be 50. And don't need locking. I'm just curious what I'm able to do on this. What can I output? So I can't do 1.0. What about 1.7? I can do 1.7. I can run it at exactly 1.7. Yeah, I can't do 1.0, apparently. At least according to this tool, but I'm pretty sure this tool has all the knowledge because I have my FPGA set up right now. Yeah, so we'll do 1.7. Right? We'll just run it at max. Okay. It's just, we won't even have this. Input clock must be, I mean, really we can just say has to be, must be greater than or equal to this megahertz and less than or equal to 1.7 megahertz, right? So the input clock must be faster than 85 kilohertz and less than or equal to 1.7 megahertz. That's directly from the spec, right? That's the minimum frequency. That's the maximum. At the maximum frequency, none of this timing information matters because 1 divided by 1.7 megahertz into nanoseconds is 588. So as long as the CS disable time, yeah, we have to keep it disabled for at least one clock cycle, but assuming that that clock is at that speed, then it's literally just, it's fine. So there is nothing here that isn't going to be clock granularity. So I think this is pretty easy. So all we need to do is we need to drop CS. T sucks is 100. Half of our period is 294. So we technically could drop chip select. We could drop chip select on a falling edge of the clock, and then the rising edge of the clock would actually be a valid clock to the chip. Now, we're not going to do that. Do we have to mask off the clock? I don't think so. I think the clock can just always be running. I don't think we need to and the clock and basically disable the clocking while... Yeah, because this is the shaded gray area. My interpretation is the clock should be able to just run. I can just do chip select only. Only do rising edges. Yeah, I mean, I can't do anything on an FPGA on both edges. I mean, you can if you set a higher speed, but like, from my understanding is you can't do both rise and fall unless you, like, literally architect the multiplier or use a higher frequency. So in reality, what I'm gonna do is I'm going to clock. When I make the decision to sample, I'm going to drop CS on the first clock. I'm then going to issue 16 more clocks, and on the last one, let's see, can I disable it? TDIS. No, TDIS is... I mean, you should be able to disable it whenever. So I should be able to disable it on the 16th. On the rising edge that I use to sample the last bit, I should also be able to disable the chip. So, okay, so I basically have 17 cycles. Technically 18, because one cycle is going to determine that I've made my decision to sample. That one will drop CS. It will wait for the next one. 16 to read them out. On the 16th rise, when I'm also sampling LSB, I will drive the chip select high to disable the chip. And then I cannot allow use of the chip for one cycle. I have to keep chip select high for TCSH. TCSH is 480 nanoseconds. That is, or 580 nanoseconds, which is almost exactly 1.7 megahertz, which my interpretation is this is saying I need to also clock, basically disable it for one cycle. Don't disable it on the last rising edge. Why not? Why would that matter? Because I'm gonna be sampling on the rising edge of the clock. Because of setup and hold violations, but if I am sampling the LSB on the rising edge and disabling CS, like, is there really a situation where the chip, like, am I not sampling it at the same time that I'm effectively sending the signal to the chip to disable it? Like, I don't know how the chip could even, like, assuming propagation of signals, I don't understand how the chip could get disabled before the sampling logic runs. That's my view. I'm sure, like, that's just maybe me trying to get too close to flying too close to the sun. But I don't understand how I could, like, the sampling requires a window stability around the clock edge. That's fair. Sampling is not instantaneous, yeah. Just add one more clock edge, yeah. Yeah, I mean, really, it's, then this becomes 18, wait. This becomes 19 clocks? 16 for the bits, 1 for disable, 1 for waiting 1 extra clock before I disable it, and 1 is waiting 1 clock after enabling it before data. So it's a 19 cycle. CSH, T sample, T sucks, acquisition time, conversion time, T data, power down. Power down. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. They disable the clock at the end? I don't know if you need to, right? T data. During this time, blah, blah, blah. CSH. It's weird that you can do this, and it, like, you get the bits in the other order. Power down. I guess power down means that it's... Yeah, because on the last falling edge, it's done, it's done doing the conversion. Yeah, I didn't sync the audio. I don't really care, to be honest. Come on, Spices. Hi, Bubble. You wanna come in? Come on in. Come on, Bubble. You not ready to come in? Yeah, he's a good boy. Who's a good boy? Who's a good boy? Yeah. Yeah, who's a good boy? Who's a good boy? Yeah, did you have fun? Did you have fun out there? Did you get some good smells? Yeah, who's a good boy? Who's a good boy? Okay. Okay. Hi, Bubbo. You eating? All right. Okay. so let's see. Oh my god, you guys are so toxic. All right. So how fast will we be running this at if we're doing the 16? So we clock, drop, 1. Don't they say 17 cycles is what you can do? Like, isn't that what we want? Is 17 cycles? You can draw it, yeah. Yeah, I'll just graph it out though. Okay, so I'm pretty sure just a straight state machine here would be pretty easy. So we don't have the parameter. We have the input clock. The input clock is 1.7 megahertz. So let's drive this clock at 1.7 megahertz. 1 divided by 1.7 megahertz into nanoseconds is 588 divided by 2. State machine with literally a counter as a state. Yeah, that's my plan. Okay, let's just drive this at 295. Generate a 1. What is this? 1.69492 megahertz clock. I found a fast fixed point 16-bit ATAN2. I don't think I need ATAN2. I think we have ATAN2 at home. Okay, so I'm just gonna output the waveforms. I know this software like has a GUI where you can analyze waveforms, but it kind of sucks big old donkey dick. Okay, let's see. Yeah, God, dude, this microphone's driving me fucking nuts. Let's see. Clock is at 0, data's at 1, doesn't really matter. Let's just do like 20 of these. And then always at pause edge, clock, begin, end. I think it's display, print, display. I think it's display. Yeah, it's display. Okay, so you can do like %d time, so that's the current time. And then we can display our different values. So let's display the clock and the data for now. Clock and data. Right, so this should output that. Oh, actually, I'm just going to do this. Always 1. Yeah, there we go. I like this more. It's just a lot fucking easier to work with. Okay, so there you can see the clock, right? And we're gonna output this to a graph. Just let me make this graph me. T log.text, and then we're gonna do catalog.text grep graph me, and output this to data.text. Okay. Oops. The line starts like this. We gotta get rid of the fucking Sed replace graph me with nothing. Does that work? Is that how that works? Oh, thank fuck. Okay. Plot dot plot. Set term QT 1440 900. Pause -1. Set grid. Set plot data dot text. Use 1 2 with line title clock. Data dot text. Use 1 3 with line data. Okay. Set X label time, nanoseconds. Set Y label, digital. Digital signal. Okay, let's see what happens here. Hey, there we go. Okay, let's just make this a little nicer. Set Y range. Let's just do -1 to 2. Just give some margins on the graph. Okay, so there we can see our square wave. And okay. Can you not get a VCD wave file? You can. This software just sucks a dick. It's ass. It's fucking terrible. I don't want to use it. This is way better. This is way better. This software is terrible. Okay. Let's do. Okay, so this is the code that I wrote before. This was dividing down the clock. But I don't have to do that. So all I have to do is initialize this. State. This needs to be 5 bits. I think this has to be 5 bits. So state. We're gonna initialize state to 0. Then down here, let's print out state. I don't know if there's a way for me to get that. Can I do this? Can I do dro.state? State? Is that legal? Can I access those? I don't have to like make them public or some shit. I'm pretty sure that worked. Okay, dro.state. Then beep bop beep boop ba beep boop bop bop beep boop bop bop bop. So the first, so we basically need, like, I want to, I mean, am I just always running this at full speed, or do I want to be able to issue, I think we'll just run it at full speed right now. So just a for loop is fine, right? Surfer is a pretty cool new waveform viewer. Does it work with just a standard like VCD output? And then we'll do integer ii for ii is equal to 0. Ii is less than 18 is our view right now. Let's just fuck. This fucking language sucks, man. If state is equal to ii, I mean, we're not doing any logic yet, so let's just not do the for loop yet. Well, we're gonna need it. Let's just do state is state plus 1. So we're gonna increment the state. So oh, yep. Is equal to I plus 1. $19. Oh yeah, you have to like put them here or some shit. I forget. Okay, so that state should be counting. And let's output the state. Plot data.text using 1.4 with line t state axis x1 y2 set x y2 ticks. Okay, so there we can see the state. The state is increasing by 1 every cycle, obviously. And it's increasing all the way up. So now what we need to do is we need to pull the input data, put clock. Really, these will become, let's see, input clock surfer. Oh, that's nice. That looks really nice. Yeah, I imagine that just works with everything then. I don't know how hard it is to get a VCD out, to be honest. I'm not gonna use something other than Verilog right now. Bruh, chill. Okay. Increase the state. If... Yeah, I think literally... Can I directly assign to Q? Is that a thing? Can I do like this? Can I assign to Q since it's an output reg? I think so. Yes. I mean, I don't want to write Verilog for a long time, but I want to write Verilog until I understand what I'm doing. Because I feel like writing a higher level language than Verilog before knowing the Verilog is probably very stupid. Okay, so we're gonna say the state machine is on 18. I think we want if here, let's try this first. If state is equal to 4, begin, state gets 0, and else begin, state plus 1. Okay, so this should count 1, 2, 3, 4. It's 4 for a cycle, then drops. Perfect. Okay, happy with that. I'm happy with that. Okay, so now we have to figure out how long of a wave that I want, and I need 16 clocks, right, to run it. 1, 2, 3, and then 13 clocks. So 16 clocks must happen when CS is low. So if we have to do 16 pulses, we have to wait 1 here, but we can drop CS on this. So yeah, let's try that. Let's oops. Output CS. I guess it's an input. Input. Or is it output? I guess it's output, right? Output reg CS. If state is equal to let's just start with this for now. If state is equal to 0, begin. CS gets assigned, and let's print this as well. Dir.cs. CS gets assigned the 0. All right. And then we got to plot that too. TCS. Yep, and that never goes high. That makes sense. Okay. If it's equal to 0, actually, if state is less than or equal to 18, I think it's 17, but we'll see. CS gets 1, 0. Otherwise, CS gets 1. And then let's just make this pulse out a little bit further. Let's go to 50. 40 should always be enough for 2, depending on where we're going to do these edges. I'm not 100% sure where we're going to do them. 28. And what am I calling state? What's the issue? Oh, because I have an end. I don't need an end there. Okay. All right. So CS is never going high. And that's because we're looping state around too much. So let's just do 20 on that. And now CS should actually go high between these. Yep, and it does. So here's CS going high. Yeah, I don't know how hard it is to get the VCS directly out of the tool. I don't know if I have to like manually instrument each of the lines or something. All I know is like the GUI interface was fucking dog shit. I'm trying to do everything in like as much pure Verilog as I can for now, just so I'm not as tied to a specific simulator or environment. So I like doing the display style debugging. I mean, it's like printf debugging, to be honest. Okay, should be able to add dump vars to dump a VCD with everything in it. Okay. Let's try it. Just like up at the top. Dump file, dump vars. To specify which one should be recorded. Okay, so you give it a dump file. Okay. I guess I don't do it here. I do it in my initial. Here. I guess by default, it does dump.vcd. Okay. If it's this easy, this is good then. Is this what I'm getting? A wolf? No. Am I getting output? Or do I need to pick waves? Dump var 0. Dumps all variables from all module instances. Dump vars 0. Yeah, it looks like you can specify them by like actually putting listing all the modules here. But dump var 0 I think is everything. Dump.vcd. There she is. Hey, look at that. Okay, this is good. This is good. Okay, okay, then I can get rid of this. And then this will have the 1 picosecond resolution, which is nice. Because this will actually do edges and not like sampling of shit, which is way better. Okay, let's try Surfer. This is just a cargo install. Cargo install. I saw it's Rust. Cargo install. Yeah, I think so. If it's in the repo. I imagine this is it. Sometimes there's slightly different packages. Cargo install path. I'm not sure. Can use it in the web. That's nice. I have no idea what the fuck that just installed. Yeah, that's not it. I don't think so. I don't think that's it. Uh, uh... Okay. Does it just run a web server? Or does it have its own UI? Or do you have to do a web interface? Build a source. Okay, I can do this. Let's see. It's standalone? Okay, good. Because I want to give it a file name. I don't want to have to fucking manually copy it into a browser every goddamn time. That's unacceptable. This is actually going to be a pretty good environment. I didn't realize I could just do this. That's nice. I'm just trying to do only pure Verilog things because I want to not tie myself into any specific IDE environment. Just not a fan of it. Just gonna be hitting a reload keyword. I don't know if browsers can read a file without like prompting multiple times. Pretty sure you have to like manually upload it every time. Okay. I don't know. That's just my guess. My view is like anytime you do something with a browser, you have to like explicitly upload. Unless it's locally hosted, in which case it might be able to use file, but like browsers really don't want you able to access local files. So usually that requires like an OS level prompt. That's my concern. I don't know. But yeah, this is going to be a really good experience. I don't know. This is way easier. I wanted a more complex project. I was trying to make this a little bit more difficult. I mean, it will get difficult because I think I'm going to need some ROM to store the calibration data for my scales. That's where it's going to get like interesting and kind of difficult. But you can access local files. You just have to grant access to the folder. Oh, interesting. Okay. I like seeing how things work locally too, though. Programs that can just build and run like this, to me, it's a pretty big deal. Yep. It runs, it builds. Okay, so I imagine I just give it dump.vcd and this will just work. The VCD file loaded. There's nothing in it. Okay. That's at least my interpretation. Oh, it's fast. But yeah, I can just hit R to reload that. That's nice. I said it loaded it. Yeah. Okay, so in this case, yeah, we'll just throw this up here. Open. Okay, the file browser doesn't seem to work great. Okay, maybe it does work. Maybe you just, oh, I hit cancel. I thought I hit back. My bad. Okay. This is FPGA. This dump.vcd. Okay, so that should be loaded. It shows up in the corner. That's nice. And it's probably reloading every time I hit R, but there's nothing in here yet. So, dump vars, clock. Let's just see. I think you have to do like 0, clock or some shit like that. Yes. Okay, so that does show up. Why is it not adding all? Dumps all variables from all module instances. Oh, maybe I have to specify the modules? Oh, wait, what's this? Null or empty file name. Test bench. Zero applies to subsequent. Dump on, dump off. Dump all creates a checkpoint in the VCD file and shows current values of all the selected variables. But that's a checkpoint. I want it to, like, record them. Oh, do I have to explicitly constantly dump these? Let's do clock again. Let's see what happens. No, I don't have to. Which one should be recorded? Can be called multiple times. All of it will execute at the same time. Yeah. Dump vars no arguments for everything? That's what I'd fucking expect. Nothing. I'm in my test bench. Dump file, dump vars. Do I have to do it first? Does it not do this until I have initialized them? No. Dump. Dumps all variables from all module instances. Why does that not work? No parens? Nope. Unless I'm getting errors, but I don't think so. I'm getting mixed signals. Initial begin. Do I have to put one up here too? I mean, I would at least expect to get the clocks. Oh, wait, that worked. Wait, what? But there's nothing in it? Okay, and then do this and it goes away. Okay, that's nice. Nice. Uh, 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 test bench. This is supposed to log this module, and it doesn't. Is it because I'm in this module? Oh, am I not supposed to give it the module name? No, you're supposed to be able to do that. I mean, we can just fucking do this. I'll just do clock and data NQ. And this will be, how big is this? 12 for Q. Too few connections. Yeah, I need CS. Just for now. I guess this is wire. Huh? Okay. Then just delete. Okay. Nice. Oh, that's nice. That's nice. We'll do this for now. I don't fucking understand, to be honest. Okay, so the first rising edge, the very first rising edge, it is okay for us to drop chip select. So CS, we can drop chip select on the very first edge. And that's what we do. So we gotta output that. CS. Hi, Smungo. How are you doing, Bubbo? You having fun? I saw you chewing on your bone earlier. We're gonna get you more bones. But you have a grooming appointment today. Are you excited to get groomed? Are you gonna be all pretty and smelly and fluffy? Yeah. Good boy. Good boy. Yeah. Do you know where you can stand to be on stream, S'mores? Hi. Yeah, look. It's you. Up there. Look. You just want to look at me, don't you? Hi. You want a kiss? Hi, Bubble. How are you doing? Yeah. Tell me about your day. What have you done? Oh, you want to lick my hand? Is that fun? Yeah, who's a good boy? Who's a good boy? Yeah. Are you, that stream. Can you say Twitch chat? Yeah. They're about as smart as you, S'mores. Yeah. Good boy. Good boy. Yeah. Who's your best little boy? Yeah, Mr. Floof. Mr. Floofy boy. If you want butt scratches, you're gonna have to move, S'mores. I can't move much. You have to reposition. I'm just gonna scratch the same spot. Who's a good boy? Who's a good boy? Are you the best boy, S'mores? Are you the best boy? Yeah. You like being on stream? You look good in 4K, S'mores. Yeah. Yeah, who's a good boy? I just tried to give eardrops to my dog. Oh, I had to do that for S'mores a bit. He was pretty good at it. Hi, Bubble. Hi. You're so pretty, S'mores. You're so soft. You're so fluffy. You know that? You know that you're the softest and fluffiest dog? Yeah. That's you. Oh, you want the butt scratch? Good boy, S'mores. Okay. We're gonna do a little bit of work, okay? Yeah, you can keep checking in. Yeah, you can have my elbow. That's good. Yeah, thank you. Yeah. Oh, hi. Hi, Schmorz. You're being needy. Ah, he's the best. He's he's so good. Hey, hey, don't make me strangle you. S'moresies. Hi, Popo. Hi. 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 Scooch, 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 scooch. Scooch, 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 scooch. I'd love to watch you play with the dog rather than this. He's just the best. He's such a good boy. Aren't you, S'mores? Aren't you the best boy? S'mores, give me a kiss. Can you give me a kiss? Good boy. Good boy, S'mores. Good boy. Make the camera bigger. No, it's time for him to eat some food. He's gonna keep nudging this right arm, though. Yep, that's what he does. He's like, put your arm around me. I want pets and cuddles and attention. And I give it to him. He's spoiled. Okay, we can drop chip select on the first state, and on the 18th state, else if state is equal to 18. I'm trying to count the bits. CS gets 1. Should I do it like this? Is this more correct? To like only assign it on like 0 and 18? Is that like more correct? And then we can do state. Do I just want to like unconditionally increase state? Is that a problem? I don't think you can do this. I don't think this is legal. I don't think this. I think I need to. I think I need to. I don't think I can do the 0 and the +1 at the same time, right? I don't think you can do that. I don't think that's allowed. DRO.state. Hey, you guys, thank you so much for the 19 months. DRO state. Okay, now we'll change up music again. Okay, so our state is it's 0 and then 1, 2, 3, 4, 5, 6, 7 all the way up. 1F is 32, and that's looping around. Yep, so I can't do that. So I have to do if state is equal to 18, again, CS gets 1, state gets 0, otherwise, and else, bam. Okay, so, bam. So now 12, which is 18, so it counts to 18, and then it's down for 1 cycle, and then we latch it back in. So CS goes high, because we set it high on this clock pulse, and then on this clock pulse, it becomes 1. You can change the data type. Thanks. I imagine you could. Let's just do signed. Oh, no, let's do unsigned. Thank you. This GUI is great. This is good. Thanks for the recommendation. I was really more worried about getting the data out, but this is fantastic. I mean, this would work in any simulator, I would imagine, right? I used to love doing like gate level designs. When I was a kid, I designed like a 32-bit serial in parallel out controller using all like 4000 and 7400 series logic on like pen and paper, put everything in a breadboard, do like oversampling. It was really, really cool. And it fucking worked, man. That was really fun. Someone contacted me once and wanted to like pay me for the design to like use it or something. I don't know. I just imagined it was shit, but maybe it was good. I did do like 2x oversampling, so I was never going to like get fucked by sampling right on an edge. I put some thought into it. It was really fun. I mean, I used to just like doodle schematics and like design processors on paper with like transistors. I've never really done Verilog, which is weird because Verilog to me is really any HDL is confusing because it's getting easier now that I'm starting to understand how they work. I think the biggest realization is to think of it like a JIT rather than a fucking like a procedural language. Like the way I think about it is like, okay, a for loop in Verilog is repetition. It's more like a macro where you're repeating something, you're repeating the logic of something. You're not actually like looping over a state variable and like actually doing Turing complete execution. Which is kind of neat because that's what's really cool about JITs is like JITs when you're emitting your instructions or fucking compilers, whatever you're building. When you do like a for loop when you're emitting instructions, you're duplicating the like logic and work and unrolling and that sort of thing. I don't know. It's gonna take me a while to get used to it and get used to like rising edge, falling edge, like when things are clocked in. Like, obviously things are way more difficult when you're running higher speeds and the actual transition times matter. But once I get the fundamentals, I think it'll be pretty easy. Consider it describing how the components are placed rather than a programming language. Yeah. Okay, so if state is 18, then, so state was 18, we had a rising pulse. Man, this is gonna make it way easier to learn. Because the way that I normally learn is I just, like, play with stuff and, like, see what happens. And this is gonna let me do that. Like, this test bench will be plenty accurate. I mean, the simulators. I mean, this is the simulator from Intel. Like, I imagine it's a good simulator. I imagine this stuff just isn't very hard to simulate, to be honest. Until you're simulating, like, actual physical rise and fall times and distortions. But simulating just the digital logic must be fucking trivial to just get correct. Okay, so state is 0, then CS goes low. So the first one's a little weird. No, it's not. First one's fine. So it's on... So at 0, it becomes 1. But it will be 1... It'll observably be 1 here. So then at state 1, 2, and 3, we discard. So if state is greater than or equal to 3... So I don't know if there's a way to, like, do a for loop with else is. I think the main struggle is scaling it across cores for the simulation. So you hit a bottleneck on single core perf, yeah. Luckily, I've got fucking really good single core perf. Luckily, I've got, like, the fastest single core perf you can get. Nearly. Which is what I always get for desktops. I mean, I've gotten a couple workstations. I've regretted every workstation I've ever bought. I'm never buying fucking workstations again. Terrible mistake. Okay, because now I can do a for loop for the different states. But the problem is, like, how do you do a for loop with else's? Is it implied? For loop else. I want to generate, like, if else. Because I know I can use a for loop to create kind of all of these things. Because all I need to do is, based on the pulse, shift it into a different position in the register. So this is begin, end, enable the chip, disable the chip, and reset the state machine. This is surprisingly nice. I mean, all I have to do, this make file, is just, it's just running Vlog, which compiles my Verilog file, and then it runs vsim on it. And it just fucking works, man. Like, which is really nice. Figuring out module stuff was really confusing to me. I kept thinking of, like, modules more as functions. But yeah, building this in the actual GUI, like building this program, it takes like fucking 20 seconds. So like synthesizing in the loop is really infeasible in my opinion. Like I need to be able to up arrow and like debug and try new things with like very small amounts of time. Like I don't like my debug loop to ever be longer than a second. In my opinion, that's like too long. Okay, so, first pulse comes in. Really, I care about the repetition. The repetition's where it's hard. Okay, so, 18 drives CS high. We set state to 0, and then on the first clock, this is actually state 0. So state is observed as 0 when this clock goes down. So we have correctly notched that for the right duration. Then we're going to, yeah, at 0, 1, 2, 0, 1, and 2, we discard the state. So 0, we drop it. I guess it's 1, 2, and 3 are the first actual clocks that get applied. Because we enable the chip. The clock just went high, but we just enabled the chip. Do I want to mask off the clock? Like, is it best practice to disable clocking? When you have, like, a chip enable? Okay, enable the chip. CS state. Ooh, I can post stories on Twitch. Who's following my Twitch stories? Okay, so 0 is discarded. 1, 2, 3, and then 4 is the first data bit. So 4, I is 0. I is 4. I is less than 4 plus 16, right? I is equal to I plus 1. Begin, and then we want to do Q. I minus 4 gets assigned with data. We can also clear Q at state 0. Q is 0. Okay, Q is all Fs. Why is Q all Fs? Oh, whoa, what am I doing? If state is equal to II, bam. There we go. Okay, so at state 0, so 1, 2, 3 clocks. The 4th clock, actually we pull in data. 5th, 6th. Sent by M. It recommends spade. Never heard of it. Okay, so this clock is enabling the chip. This one is discarded. This one's discarded. This one's discarded. This one is the one that samples data, which is high, and that puts in a 1. And then we end up with 1 FFF. This actually should be signed. 4095, and it becomes -1, all Fs. Why do you need the for loop? It's just to reduce code. It's just because I'm repeating the same if statement. I don't know. Is there a better way to describe this in Verilog? Okay, so... And then 18... So this one clocks in the last data. And then 17 needs to shut it down. A shift register? Yeah, a shift register makes more sense here. Okay. If state is greater than or equal to 4. But II is set by the for loop, right? You need the for loop to get II. II comes from the for loop. But yeah, a shift register is probably more correct, which would be and else if state is greater than or equal to 4 and state is less than 17. State minus 4. Yeah, you're right. You're right. Yeah, you're totally right. Begin Q. Do you think I can do that? No, probably not. Q is equal to Q shift 1. Q and then or in data. Is that more efficient? I imagine they'll synthesize to the exact same thing, right? I can't imagine that would synthesize differently. Okay, state equals 0. Bam. Clock comes in. CS goes low. We also don't have a reset yet, so we don't have a way to reset the circuit. Anyways, state is 0. First clock comes in. We use that to drop CS, so CS gets lowered. And state transitions to the next state. And Q, which is the output bits, gets cleared. Then we have 1 clock. Yep, we wait 1 clock cycle until this gets discarded, this gets discarded, this gets discarded. Then we clock in data for 16 times. On the last one, so we clock in the 16th bit, that gets us -1. Then we do, so that was 16. And then this last clock is state 17, which we then use to raise the chip select So we disable the chip and we clear the state, which then means we go one cycle until we disable it and repeat the process, right? Is this just correct? Should we disable the clock? When chip select is high, should we disable clock? I don't think so. I don't think that matters, right? But yeah, shift Q by 1 and or in the new data. I might, if state is 17, oh, we already duped that. And then just this. There we go. Now we have, I like kind of using only else ifs just because I feel like it makes it, oh wait, what did we fuck? What did we fuck? State is 17. What did we change? Is it because state clock? State goes 1? Oh, because we have the other states. This is kind of gross. If state is 0, otherwise if state is less than 4. I like this a little less, maybe. I don't know. Okay, so clock, drop, 1, 2, 3, data, all the way into the last data, and then we clock, disable, 0, and then the next clock drops it down. 1, 2, 3. And then we start shifting it in. I think this is fine, right? A shift register is super efficient in hardware. Yeah. If you tried to do something like 10 if branches, yeah. But I'm saying that the optimizer is just gonna know that it's a shift, right? That's what I mean. But yeah, the shift is probably more explicit. It's probably closer to it's closer to the end result. So it makes more sense. Okay, so now, yeah, I don't see why this wouldn't work. Oh, we have to set the initial state. I need like a reset line, right? State, and also state 5 bits, correct? Yes, because we go to 17. Yeah, because we can't do this. Because this is only a simulator thing. In reality, you have to actually set those. But I think everything else is defined. Because CS will be undefined until this runs, which is okay. Like, the first sample might be bad, but that's okay. I'm not worried about the first sample. Generate clock. Data. I think I want like an output. I guess I want to save the data When CS goes high is when Q is ready, right? When CS, the rising edge of CS is when Q, when the output data is ready, right? I don't need a separate thing. That tells me. Obviously, the first one is like kind of undefined, but that's okay. I don't even think this necessarily needs a reset because state from any initial state, it'll eventually restart the cycle, right? Undefined, 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 and then it eventually resets, right? So I don't think we actually need any reset line here, unless we cared about getting the first sample, right? The first sample can be fucked without initializing state, but in this case, we can safely like do this. Yeah, if we started in state equals 15, right? We'll have a couple iterations where we'll be incrementing the states, and then we'll eventually get to state 0, see as high, and then that resets the whole process, right? Like here, we have a couple pulses that are undefined, which is fine. CS goes high, we would get undefined data. And then, if state is greater than 17, it will not eventually get to... Ooh! Thank you! You're totally right, aren't you? You're totally right, because the way we do those statements. So yeah, nice. Well done. Well done. You get 1 point. Because I kind of just always want to do the add, except for state 17. If state is not equal to 17, go to the next state. Now that bug goes away. Yep. State goes all the way up to 31, wraps around, everything gets reset. Drop it low. Surfer, yeah, Surfer's really nice. 10 out of 10. Glad that you guys bullied me into it. It's really nice. I mean, this is incredible. Like, I was like debugging this all in hardware. I had no simulator set up. I did like one circuit last week without a simulator, and it was fucking tough, man. I think I could write simple circuits like this pretty easy now, but okay, so I think this is fine, yeah. We don't need to initialize state because we will correctly always loop around. If state is anything other than 17, it'll loop around or find the new reset. If it starts at 17, then we will skip incrementing it, but we'll go into this and we'll just CS drop, and that will just immediately start a new cycle. So yeah, I think this is fine. It's non-blocking, takes effect at the end of the time step. Subsequent uses of state in the same time step still use the old value. Yeah, I'm aware of that. But yeah, like what happened if I didn't have this if statement here, right? Because I have one place that needs... Oh, I don't need this. Sorry. Whoops. I have one place that zeros it and another place that increments it. And like, isn't this going to just be kind of random which one of these you get? Is that undefined? Like, what would this even say? Like, I don't necessarily know, this is fine. Because the last one is taken? Just change this to equal? I mean, that works, but I just... I need to increment this on everything other than 17 or above. Like, this is my view, because my concern is that, without that, my concern is that if I assign it 0 and state plus 1, I don't know which one it would get. I don't know why that's confusing to me, but we're assigning 2 different things. And thus, I don't know which one takes precedence. Like, is it the last one? Is it undefined? If it's last one, it's defined to be last one. Okay. Always increment to the next state. Perfect. Okay. That's all I needed to know. There will be logic emitted to make it behave like that, with multiplexers that implement those conditionals. Okay, perfect. So then, at the positive edge of clock, increment the state, unconditionally. If state is 0, enable the chip by dropping CS, and this is reset the digital reading. This is shift in data to the digital reading. And then this is disable the chip. Reset state machine. Right? And I think exact 0, exact 17... we could do this. Otherwise, if it's 17... Otherwise, if state is greater than 4... Is this okay? This is okay, right? Just gets rid of one more condition, which once again, probably doesn't matter for the actual synthesis. So at 0, drop CS down, clear the reading. If state is 17, disable the chip, reset the state machine. If state is greater than or equal to 4, then we clock in the data. So this would also happen at state equals 18, but we're just okay with this being undefined, right? This is going to be undefined for the first few clocks. We just don't care, right? And then this should repeat correctly. That goes to 1. That's the last bit clocked in. This one, it's disabled. We would sample the output register on the rising edge of CS. And then we go back. We discard 1, 2, 3 cycles. The 4th one is clocking in data, right? And that's what it should be, right? So CS, then we have 1, 2, 3 are discarded. 4th one takes it. So 1, 2, 3 are discarded. This one samples the data and stores it, right? I think this is fine. Right? And this doesn't need reset logic. You'll just have one undefined data, right? But the view is that Q should be sampled. Is that the correct word? Sampled? Q should be sampled, saved, latched. When CS goes high, this will contain the digital 13 bits. Right? Input clock must be greater than or equal to 0.085 megahertz and less than 1.7 megahertz. That's coming from the spec. So we should be able to just slow this down, right? If we slow this down, it should just work. It's just the same logic. Yep, there it is. 1, 2, 3 are discarded. Fourth one. 1, 2, 3. Yep, fourth one. Yeah. Yep. And then bink, bink. So we have 1 cycle high. And then, so what's the total length of this? Is this 18 or 17? Is this 18 or 17 cycles? Why is it so hard for me to reason about shit like this? The plus minus 1 stuff always is fucking hard for me. I think it's 18 cycles, right? So what's this sample rate? So we're 1.7 megahertz divided by 18. Helps to take in pen and paper. Yeah, that's what I often do. What am I doing? What am I doing? What am I doing? This is the sample rate, right? Kilohertz. So if I wanted the full, I'd have to run it at 17 bits, right? And what is the change there? Is that because this is, I think the reason that it can do it in 17 cycles is because this is dropping CS on the falling edge of clock, and it's raising CS on the falling edge of clock, right? And I can't do that. So I'm getting 1 extra cycle. I think that's what's happening here. I think we have to do 18 if we're doing only rising edges, but if you do rising and falling edges, you should be able to do it in 17 clocks. Right? Because you can't drop CS and clock at the same time. So you gotta drop CS, start the clock. Like, is it an issue that I am dropping CS on a rising edge of the same clock? Like, is that a problem? Could that ever be an issue that I'm, like, enabling the chip and a clock's coming in? Because it says I can't clock it for, like, the first 100 nanoseconds or whatever sucks was. Does that just mean it just is okay that I'm enabling it and there's also a clock on that very first pulse? Because, like, our case is, yeah, we're enabling the chip. Let's go further out. Here we, like, enable the chip and we have a clock. Or do we want to mask off the clock so the chip doesn't even see clock pulses except for when data is processing? I think that's what I did in this. I gated the clock. But I don't... I imagine that just doesn't matter. I imagine when CS is high, the chip's just sleeping and it just is doing nothing with the clock. Like, I don't think that would really matter. Yeah, drop that. 1, 2, 3. And is the view that the clock having a rising edge when I enable the chip just is never an issue because the chip will just take so long to boot and start such that that first edge just won't matter? Like, it's not going to see that rising edge and get mad? But yeah, then 1, 2, 3. We have to discard those 3 because there's 1, 2, and 3 that you discard, and then it's data. And then we have to do 16 or 13. So that's 16. The only way we could do 7 is we would have to use falling edges, right? That's my view. My view is we would have to use falling edges if we wanted to do this in 17 cycles. So instead, we do this in 18 cycles because we're using only rising edges, clocking in the data, raising that up, dropping this down, resetting the process. I think this is good. See you, Emil. I think that's right. Obviously, you can always use a higher clock rate, right? You can use a higher clock rate and like mask it off or like only let it through sometimes. Okay, so this should now be sampling. What happens if you do this? Does it just stay undefined forever? Yes. Okay. So I like setting it at 18. Actually, let's just do like 30. I know you can do like $random, right? Does that always give the same random? Do you have to like change the seed or something? But let's just say 30. This will cause a couple undefined clocks. Yep, undefined, undefined. It just makes that waveform look really nice, in my opinion. 1, 2, 3 discarded, clocking in data. Clock it all the way in. We get to the end. This clock latches in that top bit. It's now -1. Then we go to the next one, raise it up, and start the cycle. I think this is good. I think we're good. I don't even think we need a more complex test bench than this, to be honest. Okay, so what I should be able to do is yoink this and paste it into here. Right? Can you have a module inside of a module, or do they have to be separate? Nested, okay. Can't. Okay, so we'll move this out. Does the ordering matter of how you define these? Okay, so then what we're gonna do is we're gonna make one. What's the syntax for this? Like this. Then we gotta pass in a clock. We gotta pass in data. Data in this case is, so we have chip select, which is GPIO 2. Let's label these. Wire CS is equal to GPIO 02. Don't need this. And then sample, yup. Reg sample. This is gonna take in the 13-bit sample. Wire clock is equal to GPIO 00. Right, this is just the GPIO pins that I use to wire up this circuit. Okay. This is the ADC SPI pins. This is the actual sample data. This is assigning the LED the sample. Now we need to make a clock. The data is DOUT, that comes from the GPIO. CS is CS. Q is going to sample. Well, this is a wire. I can't do that. I don't think that's valid. Because I have it set as output reg because it keeps track. It does the register in here. Must be connected. Yeah, I think this, we need wire output. And I think I have to say it's 12-0. Right, I think that's now fine. And then I want to do always at positive edge of the chip select. Then we will do sample gets the output. That's my logic. So when chip select goes high, everything's been clocked out of the ADC, and then we save it because the ADC is going to keep overwriting, right? This is going to keep overwriting this output. So the output we need to save off to our like LEDs. Right, because the shifting is done in place on that. Okay, so now what's wrong? 148. Oh, reserve keyword. Out ADC. Oh. Illegal connection. CS to sample 5. Legal directional connection from the CF, from chip select to sample 5. To the node sample 5. Huh? $80. Truncated value is size 32. To match. Is that just the one? Q. Can I do like dro.q here? Or is that bad practice? So what's wrong with this? CS to the node. Output reg CS. CS, we're assigning an output register to... We're assigning an output register. I guess this needs to be a sign. Is that the issue? Assign GPIO to... Because this is an output. I don't know if you can do it directly like this. I don't think so. CS is not declared. Assign. Do I do this? Like that? We make a wire. We assign the wire to this. Don't we have to do the same for clock? Yeah. because obviously this is not an input. Okay, so let's go make a clock quick. I think this is the right way to do a clock. PLL. So we need to make a 1.7 megahertz PLL. So no locked output. Don't need a reset, right? Got 50 megahertz in. We want 1.7 megahertz out. How do I turn off the reset? Pretty sure there's a way to. It doesn't really matter. We can just not use it. Right. Reference clock, 50 megahertz in, 1.7 megahertz out. Huh? And this just makes it. Goes. Done. Did it add it to my project? Is generated. Do you want to add it to your project? Yes. Okay. So now I have a PLL. And the PLL is this. So then I do like PLL 0. Create the PLL. This is gonna take in clock. FPGA clock 150. We're not using a reset. Can I just how can I just not specify that? Ref clock is this. Out clock is clock. And then we want to wire clock, assign GPIO 00's clock. Right? Output 1.7 megahertz clock. Create the PLL. Then we have out goes into this. Clocks this. Is this good? Is this good? I think this is good. We got a 1.7 megahertz clock. We drop CS. We do our thing. I don't know if this is the best syntax for this, for like outputs. Is it like, do people just do this? Like, is this better? Like dro.cs here, like this? Can I do this? Does ordering matter? Do I have to define this first? CS is not declared. I don't think you can do that. I don't know the best way to actually like pass these things in and out. Always got to fill out the ports to a module. Okay. So I just make a wire and then assign it. There's no like simpler way to do that. I think the only part that's weird is since I'm using output reg. In theory, if I just had these as the regs here, then I could just directly access them. Okay. And then at CS, we sample it. That saves it in the sample. And then the LEDs are going to display the top 8 bits of the sample. So that will be the most significant bits will get displayed on the LED, right? And then I just ship it. I think it works. Looks pretty good. Let me turn on my O-scope. Let's see if I can probe the okay. Let's see. Let's probe the clock. Is this? Okay. I think this pin is clock. Yeah, that's a clock. Yep. My oscilloscope is saying 1.70004 megahertz. And let's check the chip select. Is that data or chip select? I think I'm looking at data. Yep. Yep. Chip select, I'm seeing 94.4467 kilohertz. 94.4467. And what do we expect? We expect 94.44. Okay. It works. It works. And the output looks completely reasonable. It is saturating. Let's see. What am I referencing? Ref, ground. Okay. Error on that. Yeah, I think it works. I keep getting confused why it's showing me all the LEDs blinking, but when I'm moving it, I would expect all the LEDs to just be constantly on, basically. Yeah, I mean, I'm definitely getting output. I think she's working. Okay, so yeah, and now let's see if I can hook up a multimeter and maybe see if this is accurate. It's just updating so often. I need a more stable voltage supply. Because since it's hooked up to the actual scale, the scale is moving all the time at this resolution, right? Yeah, I mean that's definitely working. Okay, so I think that is going to conclude the stream for now. I'm happy with getting that information out. Camera's gone out of sync. Yeah, it just does that, doesn't it? With time. But, yeah, I'm gonna take a break. I need to actually have like a proper lunch. It's sunny out. I'm gonna take S'mores out before his grooming. We got the output? Yeah, of course we got the output. It was easy shit. Okay. All right. So, yeah, I think that's the end of the stream. I'll probably do a little bit of experimenting with different, like, checking, like, how this behaves with the different phases. And I gotta set up another physical ADC on the board, because right now I am only looking at one phase. But I kind of want to, like, try and get this into RAM so that I can save the information that I have and then take that somewhere in software so I can, like, look at what this signal looks like. Because I don't really want to do this fully blind. I'd like to be able to see kind of this signal, but we'll see. Is it running the scale? Yeah, it's running the scales. It's just ADCing. I already kind of basically had this with the previous code, but now we have this nicer module that we actually tested. But yeah, I gotta get S'mores ready for his grooming, and I'm gonna keep fiddling with this though today. I want to get it counting at least. I want it counting. I might play with some of the HDMI output as well. That's gonna be kind of fun to play with. I think it's really easy. I think I just output 24 bits at a time in parallel for the RGB, and then a VSync and an HSync, or an HSync and a VSync. And I think it will just give me HDMI out, like raw HDMI out. That might be really fun to play with. I don't know how hard it would be to make a frame buffer. I imagined I'd have to use, like, actual RAM. I don't know how much RAM there is on this. Total block memory bits. I have 5 million bits on the FPGA, and that's not enough, right? I'm gonna need 1920 times 1080 times 24. I need 49 megabit, like 50 megabit. So I would have to use the actual RAM. Or I can just boot it into Linux. I haven't played around with the Linux side of things, the SOC. I don't know how hard it is to get data from this over to the SOC. So what's interesting is that I don't need to get this high frequency data over to the SOC. All I need to get to the SOC is I need to get it the current 20 micrometer displacement. So I'll do the edge detection in the FPGA so that I know what the current 20 micrometer displacement is, and that will just be like a number that's like the absolute position of the scale, and then just the most recent sample. And I could literally send that 60 times a second, and that would be more than I would ever need, because at the end of the day, I have to render a number on a screen, and the fastest I can update that is 60 hertz, or, you know, however fast my display is. So in reality, all I need to do is, like, keep count, and my plan is probably not to do the actual like tangent, like that sort of logic in the digital space. I plan on only doing that in in the FPGA. I plan on doing that on the software. So that'll make it easier for, like, RAM and all sorts of stuff. So really the plan is to, like, take this, do edge detection, save the data, and then send it over fucking 10 kilobaud over to the as raw data over to the SOC, and then we can build calibration data for the scales. Because remember, these scales are not 1 volt peak to peak everywhere like they should be, because there's damage on some of them. So there are some low spots, and I think the best way to solve this problem is literally just calibrate the scale. Like, literally do one sweep of the scale, record record the lows and the highs. So like calibrate it, button it up, don't touch the pot ever again. Sample it, so I record like, basically I just need to record the amplitude of the sine wave for each 20 micron. It's really not that much data. And then that will tell me the true expected amplitude, and that's what I'll use to correct the fact that the scales are dimmer in some spots than the other due to physical damage. That's the plan. And I'm not going to do that in the FPGA. It'd be doable in the FPGA, but you're going to need RAM or like ROM. No, we ain't doing that. So we'll do that on the SoC. I haven't played with the SoC. I'm going to have to figure that out. So anyways, that was pretty fun. Getting the simulator set up in a basic way. That was kind of cool. I mean, I think this is a great example, hello world. In reality, I'm pretty sure you just go and click one of these library things and get the one that talks spy. But it's just kind of fun to like think through the logic yourself. This is so easy to set up. I imagine this would take me 5 minutes to ever do this again in my life. So, anyways, thanks for stopping by. Hope you had fun. See you around. I'm gonna go eat some Mexican food.